Hello everyone. How's the audio? If you can hear me, that'd be great. If not, I will adjust something. Okay, let me see. No, send that notification, do that live. Okay, so you guys can hear me well? I need to get a better thumbnail, but I will handle that later, I guess. Alright, cool. So, let me pull this up then. When is that? 3 p.m. Okay. I guess we will try and finish before then. Alright, so I guess what I could do is, since I did release the video beforehand, maybe I could like start this off with a question period or something. So if you have any questions on the material, I guess I'll take those now. And then you can, of course, ask me anything like during the stream, and I'll answer them generally between problems. So yeah, is there any questions you guys have on the material, first of all? And then we'll get into the problems. Now, you may notice that I have solved many of these, and this is just because I handpicked ones that I knew were good. And so to know that they were good, often it required me to solve them to actually figure it out. Okay. I don't see anything. So there were no questions on the material? Or I guess we can get to them later. Just waiting around now. Should we just get right into the problems then? Can you guys still hear me? It's working, right? Video resolution is fine. I don't have a better choice for that. Yeah, I am aware of the cook-offs. That is not something that I could really avoid. This was like the only day I could actually do it. Okay, so we'll just get right into the problems. Let me donate. Wait, is that not an option? Monetization should have enabled Super Chat. I'm, of course, not asking anyone for that, but that should theoretically be an option. Is it not? I don't want to set that up, if that is a thing. Can't tell. Okay. That is good to know. Okay, so how many stars on Code Chef? I currently have 7, though I'm barely at that threshold right now. Alright, we'll enable this live, sure. I was going to put this in anyway. I'm pretty sure this number is not accurate because of various reasons, but I'll just use it anyway. So monetization, yes. And then supers. Oh, okay, I just do that. I did not realize that was a thing. Okay, that should be good now. Yeah, okay, I looked at those like options. I didn't see that there were explicit like checkboxes and stuff. Can you explain how mod 2 to the k and with 2 to the k minus 1 same thing? Yeah, sure. Okay, wait. Let me get my tablet because I actually am disorganized. I didn't get this yet. You're welcome for that. Alright, I'm back. Sorry about that. So, yeah, that is a good question. Okay. Slightly a mess right now. Apparently I dropped my laptop in the middle of the night, so all of my like beautiful setup got offset. Just kind of a pain. Alright, I've been using OneNote. I think there are better options, but I'll just stick with this for now because it's like what I'm using. So, mod 2 to the k is essentially asking for, let's say we have some number like, Nope, there's no 2 in binary. That's an important thing. Right, and so we want this modulo 16, for example. So modulo 16 is essentially saying we want the last 4 bits. Because these last 4 bits represent the remainders from 0 to 15. Everything else is a multiple of 16. And therefore we don't care about it in the mod. So all we're asking for when we do mod 16, or in general when we do mod 2 to the k, is the last k bits. So in this case we want the last 4 bits. And the way to get the last 4 bits is, essentially we use the bit mask where everything is 0 except for the last k bits, which are all 1s. And the reason that works is everything that's 0 will just be eliminated, because and 0 is always 0, no matter what. And the things that are 1, well, anything and 1 is itself. So the bits that will be kept are only the bits that we want to keep, the last k bits, and they will have their original values. So anding with 2 to the k minus 1, which is like this number that has the last k bits as 1, is what we want. Does that make sense? Might have to refresh the stream if you want to. Okay. All right, any other questions, or I'll just jump into the problems? I think I can erase this. Advent of code. Sure, if it's popular. Yeah. I am fine with doing that. I'm not the fastest anymore, so I will probably not be able to get the best times, but I can try. Um, 743. I did that round and then it got unrated, and then I didn't do C because I totally lost interest in it. So I probably won't make a video just because, like, first it's unrated, second it's already way past the round, and third, like, I didn't like the problems anyway. So it's just like a combination of stuff that wasn't enjoyable. Also, since when is 2 problems enough for IGM performance? That's not supposed to happen. This unrated thing is really messed up. Logical thinking. I mean, I don't know if there is another way. Like, another way than solving problems. I mean, really, like, you just need to jump in and get the practice. You need to train your brain that solving problems is what you want to be doing. Didn't seem like my type of competitive programming. Yeah, you are somewhat right about that, but I'm more of a sellout now, so I'm willing to do it. Yesterday's Div 1B, we can do that at the end of the stream. Right now I want to focus on this. And left shift, I recommend left shift. POW is weird because it sometimes, if you use doubles, then it's just going to have really big problems. So don't use POW with doubles, and also, like, left shift is faster, so it's better to do left shift. Just left shift or right shift for division. I think the compiler will optimize out right shift, but maybe. I don't know. But left shift is, like, effective. Alright, now we have a bunch of questions. Now, as I say, we're going to start. There are problems which I don't understand even after seeing tutorial. You can either try and read in the tutorial a couple more times, or there is just a chance that maybe it's too hard currently. That could also be a thing. I mean, often I don't understand the tutorial the first time I read it, or even after multiple reads, so yeah, it could be worth just spending more effort to try and parse it and break it down and understand it more. Especially if you think the problem was interesting. Have I practiced Python? I have not. Okay. I'm gonna let's see. Oh yeah, mashup link. I will. Okay, go away, YouTube. I will link that right now. That is a good point. By the way, this is a tutorial video I made. It has like context for this stuff, so I can copy this link. Make sure that. What the hell? Okay, wait. Okay, wait, hang on. Something's messed up here. I just want this link. There we go. Alright, so I can pin chat. I do have the way to do that. Wait, what? Does that link work? Does work, okay. Guide from expert to CM. I will make a ladder video, or I'll make a ladder series eventually. Right now, I don't know enough information to do the lower ratings. But when that does happen, I will try and make a ladder series. That is something I'm thinking about in the future. Average rating? You can see the exact ratings. Wait. I'll put that here too, actually. I put a bunch of stuff in the old video. The video that's like the tutorial. Oh, come on. So this is the difficulty distribution. I put it in a paste bin so it's not going to be spoiled. Okay, I'm setting up the stream as we're doing it. This is a very good setup. Let me see. So copy this again. I help you win a regional contest if you donate $50. No, that is not how that works. Even if you donate, I will not help you cheat. That is not something I want to do. So don't donate, because that would make me feel guilty. And I would just feel guilty, but I'm still not going to help you, so don't. Okay. Any other questions? I'm hyping up this problem very much by avoiding doing it. By the way, this one's only rated 900, so many of you should be able to do it. The early problems are, I think the first three are designed to be fairly easy. I don't understand how D has so many solves compared to the other two. What would I do if not related to programming? Like on YouTube? I don't really know. I don't have that much else that I'm like actually passionate about. So programming is the best thing for me. I don't really know what else I would do. I mean, sometimes I play video games. You can see BTD6 in the background. That is something I'm currently slightly addicted to. But not that much otherwise. I don't really like get that much free time. Okay, I don't want you to pay me to cheat on a contest. Please don't do that. I mean, there are other people who are willing to do that. I don't condone it, but I'm not the right person anyway. How did you do an ICPC? I don't know. Okay. Before we start we're going to continue not starting this problem. And I can go on a rant of ICPC. So my ICPC situation. The way it works in my university is, I know in many places you pick your own team, you register for yourself, find a coach, whatever. At UMD, which is my university, It's a school hosted contest. It's like a long contest. Whoever the 3 people that do the best get on the A team. The next 3 people get on B team, and however many they send. And so that's not happening until like February, when it's the guy I emailed said closer to the start to the contest. So I have no idea who the team is. I don't know like anything about what we're doing this year. So I'm just kind of like in the dark. I know one other guy who's doing CP, but like that's it. So I don't know how we're going to be able to practice like that. So that is very unfortunate. There's not much really I can do about that. And I don't know how to meet other people in CP either. I don't know like who they are. Everything's a mystery. You know, actually, if I search this up, I'm pretty sure, like, there is a comment about people who did ICPC. And it's by some master. And this is, like, cool, right? It's like a master, so maybe that's interesting. And then, as it turns out, he's from some university in Iran. So, and his last visit was 16 months ago. So I don't know what to do about that. These other guys don't have handles. I just know nothing. It's kind of annoying. Why UMD? I didn't have another choice, that's why. Good resources for DP and graphs. I do have streams on both of those. You can look those up. I'm sure there are others on YouTube as well. You can just learn the material. And some people have code templates. Like this guy. This guy has been doing some great stuff. He has like... He just created this library with like literally everything. Like it has literally everything. There are Reds that are commenting that they couldn't suggest anything else. That's how extensive this library is. So I recommend using this. I'm sure it's pretty good. Okay, what did I miss? Did I play Valorant? No. I'm not exactly into those types of games. Did I do round 743? Yes. Kind of. Kind of, in that when it became unrated, I knew how to do C mostly, and then I just lost interest. So my rank is like fairly good. It would be enough for a rating change, but again, because it's unrated, all the ranks are meaningless. People gave up midway, etc. So like, there's no way to really deduce how good my performance actually is. Is there a FIDE for chess? Or for competitive programming? I think the best is ICPC, but if you want like an official rating system, I think Codeforces is like the most respected rating system, at least like globally. There are others like AtCoder and probably not CodeChef because people sort of laugh at it, but I guess Codeforces is probably the most universal one. Why not Twitch? Because I want to grow my YouTube. Actually, I was thinking about doing multi-streaming. I'll try that later. Haven't done Snackdown. No, and I don't know if I'm actually going to do that because it's single and that sort of ruins the whole fun. And I don't have a chance of winning prizes anyway because I'm not going to make finals. I'm not that good, so it's sort of unfortunate. All right, yeah, we should get started. All right, last question, then I will reserve everything else for after this problem. I will answer questions in between problems. Who is your favorite YouTuber? Second Thread, for sure. He is like the most entertaining guy on... He's like definitely the most entertaining competitive programmer I've ever met. And it's just like fun to watch. So yeah, Second Thread if you haven't seen him. Okay. Yeah. We're gonna do this problem now. Mocha is a young girl from high school. She has learned so much interesting knowledge from her teachers, especially her math teacher. Recently, Mocha is learning about binary system and very interested in bitwise operation. By the way, this is a Div 1A. Div 2A. Like, literally, they're putting bitwise stuff in Div 2As. So it is definitely a hot topic if you don't know much about this. Did Second Thread pay me? No, he did not. This day, Mocha got a sequence A of length n. She can select an arbitrary interval LR and do some weird thing to it. You can, the way this operation works is essentially you pick like some indices, like a range of indices or something. And then, so this is like, essentially, on this range, you're going to, like say you have 1, 2, 3, and 4. What you're going to do is you're going to pair up the opposite indices. And then you're going to replace A1 with A1 and A4, like bitwise and A1 and A4. And you're also going to set A4 equal to that at the same time. So both of these are simultaneously set to this value. You do the same thing for, holy crap, Oscar, thanks for the donation. Wow, you actually did it. I really, I really hope, I cannot do that sort of thing, but thank you for the donation. Thank you for the appreciation. That's nice. I'm sorry, I don't exactly know what currency that is. I know some YouTuber always messes up pounds and euros. So I'm not gonna risk that yet. I will eventually make that association, but not yet. Okay, so euro. Okay, thank you. I'll try and remember that. So euro is like the croissant. Sure. Okay, so this is how this works. So this is the way these operations work. So this is like a weird operation, but one way to think about it is consider if you select two indices, like for example 1 and 2. Then essentially you're going to basically bitwise and the two together. So you're going to set A1 and A2 to A1 bitwise and A2. And so essentially you can bitwise and any two indices together. So something I mentioned in the video I made, bitwise anding is always going to decrease a number. And what you want to do in this problem is you want to make every number as small as possible. You want to make the largest number as small as possible. So because bitwise and is always going to decrease a number, what you might as well do is you might as well and all the numbers together. So the way this problem works is, let's also consider another theme. Bits are independent. Bitwise and works on bits independently. So if you have two numbers like this, each bit is going to be treated independently from the other bits. So this is 0, this is 1, this is 0, right? And these are just totally separate. So if we consider that, we want the number to be as small as possible. So for an individual bit, we want everything to be 0. And the only way we can make everything 0 is if we have at least one 0 in this array. And if we do have at least one 0 in this array, then we can sort of like say we have a 0 like here. Then we can do the operations like this. We can, for example, do a single operation like this, and then that will bitwise and this 0 over to here. We can do another operation like this. This will make this 0 over to here. And we can do the same thing. We can make the whole thing 0 for that bit. So if we have at least one 0, we can make the whole thing 0. And if we have all 1s, then we're forced to have a 1. So that will be our answer. The answer is for each bit independently. If we have at least one 0, we can make it 0. And if we have all 1s, then we have to be 1. Now you could stop there. That could be your implementation. But notice that that is exactly the definition of bitwise and. If you have at least one 0, you get a 0 from bitwise and. If you have all 1s, you get a 1. So really, what we're doing here is we're really just bitwise anding all of the numbers in the array together. That is the final part of it. That it turns out that the answer is exactly the bitwise and of the whole array. Now, another way to arrive at this conclusion is basically like you can just sort of intuitively think that if you do enough operations like on the whole array, like you just keep spamming operations over and over, eventually you'll get to a point where like everything is equal to the bitwise and of the whole array because you can just and stuff together as much as you want. That's another way to think about it. But ultimately the answer is the bitwise and of the whole array. That is the best you can do. Does that make sense? So coding this is incredibly simple. We're going to read in test cases. So cin do n. So we're going to read into the array. And then we're going to start with the first number, and then we're just going to bitwise and everything else with it. If I can type, that would be cool too, to be able to do that. So yeah, any questions on that one? I feel like I kind of went a bit fast on that actually, so if it's confusing, feel free to ask something. Also, I'm not in manager mode. You should be able to see my submissions. If you can't see my submissions, please let me know, because I want that to be possible. Does that make sense? Also, we have more stream viewers than likes. This is a slight shout out to myself that you should like the stream, because that increases engagement and more people will watch it. Just saying. Just pointing that out. Yeah, hi everyone. I am also a fan of myself. Thank you for that. Okay, any other questions, or should we move on to the next one? Make it increasing is at the end of the stream, so you're gonna have to get through like all of these. Have fun. Apparently nobody has bothered to do it. I explicitly mentioned one person who's solving the later two problems that they should not do M because it is not going to be worth it. And I stand by that. M is not worth it. So that should not be a thing. But I put it on sort of to torture myself. Yeah, thank you for the likes. Awesome. Awesome, awesome. They told any interval means we can take each element as an interval. Yeah. Yeah, we can take each pair of elements too. We can like take any interval we want and we can do the operation. If you do it on a single element, it doesn't make sense because you're just ANDing it with itself. How long is this stream going to be? I'm going to do all the problems on this mashup. That is how long it'll be. I'm aware there is cook-off. You guys feel free to leave. Feel free to leave and do that. Like the stream archive is going to be up anyway, so ultimately you'll have a solution to all the problems no matter what. So if you do want to leave for cook-off, feel free. That's going to start in roughly an hour, I think. So you don't have to leave immediately. You can wait till then. $150. That is indeed my name. Okay. How to become like me? Practice. I'm actually gonna release. I'm planning a short. How would you feel about this video? I'm gonna call it 3 practice methods in 60 seconds. And so it's gonna be like, I said I would make my last video short, and then I didn't actually make it short. So this one, I'm guaranteeing I'm gonna make it short. No, you're my first donation, which is cool. I haven't streamed. This is my first stream since I enabled monetization. So this is the first time. You have made history in a sense. I did not do Kickstart yesterday. I was tired after 7:43. Yeah, congratulations again to Oscar for being the first donor. That is very cool. Alright, I don't see more questions. Let's do this problem. It'll be pretty quick anyway. So Baby Badawi, I don't know how to pronounce that. Baby Badawi's first words were and 0 sum big. So we decided to solve the following problem. Make an array with and 0 and a big sum. So all its elements are k-bit integers. That is the first thing. The next thing is the bitwise AND of all the numbers must be 0, and the sum of the elements must be as large as possible. And you're creating an array of length n that does that. Okay, first of all, bitwise AND is 0. Once again, we're going to repeat the idea over and over that bits are independent from each other. That is a very, very, very common problem-solving idea. Bits are independent when you're doing bitwise operations. It is live, by the way. Bits are independent when you're doing bitwise operations. That is so important. Always consider that. Always consider if you can use that idea or not. And in this case, we can. So the bitwise AND of all the elements are 0. So suppose we're working with 3-bit numbers. Well, for us to have the bitwise AND be 0, we need to have at least one 0. So for example, say we have 4 numbers, and we have 3 bits. So let's consider this bit. We want the bitwise AND to be 0, which means we need to have, so if the AND is equal to 0, at least one 0. That is the condition. Now, what if we need more than one 0? For example, suppose we did something like this. But then, because we want the bitwise n to be 0, but we want the sum to be as large as possible, for the sum to be as large as possible, we need to do better than that. Because we can make this 0, 1, for example. The sum will increase, the bitwise n will not change. And in fact, the best thing to do is to make it so we have exactly 1, 0, and everything else is a 1. And that will make the sum as large as possible. So for each bit, we want exactly 1, 0. For each bit independently. And the reasoning is that we can't do better, because we need to have at least 1, 0. And if we had more than 1, 0, then we could do better. So we would always make it 1, 0 eventually. We would always increase the answer until we're left with 1, 0 in each bit. So this is the criterion. Every bit is going to have exactly 1, 0. Now, the question is, where do we put them? And the answer is, we have n elements. Each element can be the one that has a 0. And each bit is independent. So we have n choices for the 0 in the first bit, n choices in the second bit, n choices in the third bit, etc. We have k bits in total. So we have n choices k times, so the answer is n to the k. So in this problem, the answer is simply n to the k. K is 20 because you can I don't know actually. I don't know why it's 20. But the answer will be n to the k. This also requires modular arithmetic, but modular arithmetic in this case is simple. You just need to mod the answer a bunch of times. Okay, so let's just do that. So ants is equal to ants times n. K times are going to multiply by n, and then we're going to mod it by the mod. The mod is up here. It is 10 to the 9th plus 7. Be sure you do not mess up the number of zeros. One thing you can do is you can use something like is 1e9 plus 7. That will also work for C++. I don't know about other languages, but it works for C++. So that is something you can do if you don't want to mess up the number of zeros. I have this in my template, so I always make sure it has exactly 8 zeros, 1 1, and 1 7. That's easy to mess up. Anyway, we're multiplying by n k times. We print that out. I'm so confident, I'm not even gonna test it. Is that a mistake? Probably is a mistake, but we'll see. There we go. Okay. How to become red coder? First of all, practice. Second of all, practice effectively. Third of all, again, I'm going to make a video on that, and there are also a bunch of other videos on good ways to practice. But there is no way around it. You need to practice. You need to develop your problem-solving skills. How to improve skill? That is a good question. Starting off, the best thing to do, I guess, is learn basic math, because a lot of problems just require sort of logic and stuff like that. Honestly, I'm not sure the best way to teach starting out. I think that's something that's best learned in school. School will just ingrain the intuition in you of how math works, and then you'll be able to think about problems like that. But I am not exactly sure the best way to actually start off. That is one thing I've not been able to figure out. Can I please zoom in? Yes, I can try that. How? Okay, I'm going to view. Can I zoom in? I can increase the font size. Is this good, or should I make it a bit bigger? Okay, sure. I mean, yeah, it might teach you to be a calculator, but what else do you start off with? Do you have if you have something better, please tell me, because I don't know. Figuring out the way to start has been the hardest thing I've been thinking about. You just need those basic problem solving skills, or the basic the way to think about logic. Can I explain again? Which part? So we're looking at each bits independently. We're looking at each of the bits independently. We want to maximize the sum. So we'll think about maximizing the sum of each bit independently, right? And for a bitwise AND, the condition is you have at least 1 0. So for each bit in the array, like you can consider, the way I'm sort of describing this is we're going to consider the array as you have k bits and you have n numbers. So we'll think about like a k times n matrix of zeros and ones. So think about it like this, for example. How many girls have you actually asked about my hair? I would like to know the answer to that. So we're sort of like filling in this matrix. And then to get the actual numbers, we're just going to like go down the columns. So this is going to be the bit representing like 2 to the 2. This is 2 to the 1. This is 2 to the 0. This is the way I'm thinking about this problem. Maybe that wasn't clear before. So we're going to do, for example, this. And this is going to be the numbers. This is A1, this is A2, etc. Right? And so we're thinking about what we want to do to make the sum as big as possible. Oh shoot, I forgot to update that. This is problem B. That is my bad. Does copying this work? Sorry, that is my bad. I'm pretty sure that link will not actually work. So yeah, we're thinking about this like a matrix. This is another like separate way to think about like filling in bits with a number. Because bits are independent, it basically is like a matrix. You handle each rows differently. You handle each row independently. So yeah, within this matrix, again, for the bitwise AND to be 0, we need at least one of the zeros. We need at least 1 0 in each one independently. There's no reason to have more than 1 0 because then we could get rid of it, increase the sum, and leave the bitwise AND the same. So we might as well do that. So instead of having at least 1, we'll just say we have exactly 1. And to have exactly 1 0 in each row, the only thing that differs is where we put the 0. We have n choices to put the 0 in the first one. We have n in the second one, we have n to the third, etc. So we have n to the k. I'm not sure, is that better? I think that might represent visually how I'm thinking about it. I'm gonna have a field day with these timestamps, huh? Okay, I'll leave that for now. Dijkstra and the easiest way. I do have a thing on that too. Let me see. I have an implementation for Dijkstra. Let me just pull that up. You can find that here, galen-cp-templates. That link is directly in the description if you want it. I have a template on Dijkstra that I scrolled past. Like essentially it's just doing the greedy part. You're looking for the farthest edge. If you don't understand Dijkstra, I don't have the best, I don't think I've ever done an explanation on that, but I'm sure like there are other tutorials for that can explain it already. I guess. I don't remember if I did that explicitly in my graph stream, but I did do a graph stream. That could be a good reference too. Some of the problems were Dijkstra in that one. But the way my template works is it handles all the heavy computation. All you need to do is give it the graph. You just pass the edges you want, and then you give that to it, and it will handle it for you. Okay, let's do C. Audio quality has got much better. Thank you. That is my Mac mic at work. I did not click this. Okay, come on. Just go away, YouTube. The video resolution is a problem. Yes, I get it. There's nothing I can do about that. That's my Mac. You've done a super chat, but it hasn't showed up? I'm not sure what to do about that. That seems like that might be a YouTube problem. Yeah, I haven't seen it either. That's not good. Math for competitive programming? Mostly basics. I don't know where to learn math, to be honest. There are sites like Brilliant and stuff like that, maybe Khan Academy. There are a bunch of free sites that do a lot of work. Yeah, okay. Slight detour towards Dijkstra, and then I will get back to this problem. Or I will start this problem. To pass the graph, essentially, like, the graph is just a list of edges. Like, it's a list of edges. Like, an edge is an edge from A to B with weight W. If you want undirected, you would add an edge from A to B, and you would add an edge from B to A. So it just goes both ways. So a graph is a list of 3 tuples. The node you come from, the node you go to, and the weight. Right? And so all you need to do is tell the template these tuples. You will tell it to add these edges. In my template in particular, you just use this edge function. It will do an edge from A to B with weight WT. If you want, this is by default directed or undirected. If you want it to be directed, get rid of the part that goes back. Just delete this line. I'll update that later. I plan to eventually clean up my templates. That has not happened yet. I will make it so it's more user-friendly. My segment tree is disgusting. I will make it better. But it's not better right now. But by pass the graph, that's what I mean. You just give it the edges that you want. You just add each edge manually into the template by calling that function. And you also have to initialize it. I always have like an init function that creates vectors and stuff like that. So this is n. This is the number of nodes you have. Okay, are we good for C? I'm able to solve with 1500 to 1600. Whatever you've done to get to the point of being able to solve 1500 to 1600, keep going. Like that whatever strategy you had to get to that point, just keep using it. It's probably going to keep working. But if not, again, I'm going to make a video soon. I keep referencing future videos, but really, I'm going to make a video on practice methods. And but I guess the best thing to do right now is just to solve problems that are hard for you, problems that take a while. If you have a better template, feel free to send that too. I don't think it allows links, but you can get around that, just like split the link into pieces or something like that. Can I teach some of the important math topics? Maybe in a different stream, not this one. That's not how what works. Okay. All right. Let's just do this problem. Let's actually do this problem. I'll move questions again to after. So, I'll go over the brief statement. You can get rid of the story here. You're given an array of length n. The task is to calculate the number of pairs where the bitwise AND of the two numbers is greater than the bitwise XOR of the two numbers. Yeah, AND is greater than XOR. That's it. N is 10 to the 5th, so obviously you can't compare it directly. So let's figure out how we do this. And how exactly do we do this? So, the problem A, no, what? Problem C, what am I saying? Okay. We're gonna look at two numbers. Let's think of like 5-bit numbers. Even though numbers do have more than 5 bits. But let's just consider some. Like for example, 10110. No, I'll do it this way. So I do like A1, A2, A3, A4, A5, A6, something like that. So like 10110, just fill in some random numbers. Right, okay. Also, the bitwise AND has to be, oh, actually, it can't be 0, so we'll make it 1. Bitwise AND is greater than or equal to the XOR, but it's always going to be greater than. Anyway. So let's consider two numbers. So first of all, the bitwise AND, once again, just to rehash, bitwise AND is true. It goes bit by bit, and it will output a new number that will reflect on each bit of the new number will represent if both bits were 1 in the two numbers, then it will be a 1. Otherwise, if at least one of the bits was 0, in this case this is 0, it will be 0. So the bitwise AND here would be this number. Bitwise AND of these two would be 0 everywhere except for this one, and so on. If they're both 0, it's also 0. So like this would be the AND of these two. Right, so yeah, this is how this is going to work. And the bitwise XOR will do the same like sort of bitwise stuff, but instead of representing if they're both 1, it will represent if the bits are different. So if this bit is, if these two are the same, it will put out 0, otherwise it'll be 1, etc. So when is the bitwise AND greater than the bitwise XOR? And here, we're going to rely on another philosophy of bitwise problems, which says that another thing that's very important. This bit is going to be worth more than all of the smaller bits combined. The highest bit is worth more than any smaller bit, like when you add all of them, all their contribution together. So if you have the option to take any bit over all of its like smaller bits, take that bit because it's going to be better. So in this case, what's really happening here? We want the opportunity to, well, we want the bitwise AND to be greater than the bitwise XOR. So it may help to consider like a truth table. In this case, it would be something like, so like A, B, we just go through the cases and see what happens here. So this is A XOR B, this is A and B. So for example, we have 0, 0, 0, 1, 1, 0, 1, 1. So A XOR B is 0, 1, 1, 0. A and B is 0, 0, 0, 1. So only when we have 1, 1 will we actually get 1s. Only when we have these will we get XORs of 1s. So we want the first, so notice that these are completely different. There is no set of bits where the AND and the XOR will both be 1. There's no set of bits where the AND and the XOR will both be 1. So really we're interested in, for the first 1 that appears in the bits, does it belong to the AND or does it belong to the XOR? If it belongs to the XOR, then the largest 1 in one number is different from the largest 1 in another number. In this case, the largest ones are not the same, so the XOR will get the 1 and the AND will not. But we want the AND to get the 1. So in this case, here the AND will get the 1, the XOR will not. So who wins the battle? And really, all we're focusing on now is the highest bit of each number. Or as some people would say, the most significant bit. Because we're interested in, are they the same? If two numbers have the same most significant bit, then the AND will be 1 before the XOR will. So the AND will get the most significant bit, and the XOR will not, so the AND will be greater. And if they're different, then the XOR will get it. Like this is a 1, for example. So now we're just counting the pairs that have the same most significant bit. And counting pairs of something that have the same as something is fairly easy. What we do is, we'll count up like the number of numbers that have the most significant bit be I. And then the answer will be sigma or sum of ci choose 2, which is the number of ways to choose pairs from these numbers, which is equal to ci times ci minus 1 over 2. That's just the formula. right? So yeah, so we need to find the number of numbers with the most significant bit. So like mainly the computational part now is computing this part. There are a bunch of ways we can do this. I think built-in pop count is the wrong one. There is, I had this as a practice problem on my tutorial video, which again you can find right here. Like it's there in the description. But the number of numbers with the most significant bit being I is, we can count that with a function. And the function here is, I don't think it's pop count. I think it's, we want the number of leading zeros, essentially. Let's consider like an 8-bit number now. Let's say, for example, we have something like this. So the bit positions are here. There's a built-in function that lets us count the number of leading zeros. In this case, there are 3 leading zeros. There are 3 zeros before there's any 1. And so in this case, the most significant bit is offset from position 7 by 3 bits, because there are 3 zeros before we get to the 1. So the answer here would be 7 minus 3, or in particular, 7 minus leading zeros. And yeah, the way to do that is with a function called underscore underscore built-in CLZ. Note again, there is a specific long version of that, which I'm going to use because I always use longs. And so because it's 64 bits, here the formula I would use would not be 7. It would be the number of bits minus 1, which is 63. If you were using ints, like the integer data type with 32 bits, you would use 31. The number of bits minus 1. In particular, it's how far from the last bit are you? So yeah, essentially we're just going to do that. We're going to read an n. We're going to create a count array of their numbers up to 10 to the 9th, so the values are up to like 2 to the 30th at most, because 2 to the 30th is a big number. So we'll say the count is like 50 or something. We just need some number bigger than 30. So now we're going to read in the array values. We're going to find the most significant bit using this formula. In this case, it's going to be 63 minus... As it turns out, because we're just, all we want is to categorize by the most significant bit, we don't really need the exact formula. We can just group them by the leading zeros, but in this case, like, it's fine. It doesn't matter. I'm just going to use the exact number because we might as well. So now, increase the count. So then the answer would be count I times count I minus 1 over 2. Be careful with overflow here. This can overflow. Like this formula can overflow because it's 25, it's 25 minus 1, that can get up to 10 to the 10th. So be careful with that. This could potentially overflow if everything has the same most significant bit. Is my camera fine? Yeah, okay. I'm still on. Is he a lady? No. Yeah, built-in CLZ. You are not that late. We're only at C right now. You just missed the introduction and stuff like that. Did I learn discrete math using online resources? I took a class in school, but that was only recently, and I still, like, by then I was still international grandmaster. So, like, that was not necessary to get me that far. Discrete math is not what carried me through competitive programming. Math for CP. I still don't know where it is. Maybe Everrule has a better answer for that. But let me think about that one. Maybe discrete math is a good way to go, actually. Discrete math might be the best math to learn for programming. So I would think about that, I guess. Say your name. Hi, Shibam. Sorry if I botched that. I know I'm not good at pronouncing names from various countries. I will give that a warning in advance. So, will I ever make a stream on number theory? If it wins. And actually, I hosted the poll via YouTube comments, and because I don't have much progress on my alternative, I might just have to do that again. But this was the poll. Okay, that was loud. This is the poll, and I basically just had people voting comments. This took over, but this had won beforehand, so this was the thing I did. And number theory got a good number of votes, so that could potentially be another stream. Missed ABC? Okay. You will be able to watch the stream however late you want. I can say code with GD, yeah. The last name? I'll try Shivam Kushwa. Is that how that's... How would you pronounce that, I guess? That is how I would pronounce that with my tongue. Okay, I tried. Gave my best effort. I want to use dark theme because I'm used to light theme. Practice problems. Try the things you can't solve. Like, just practice stuff that's at B level. And put a lot of time into it. Don't give up that easily. Number theory, that comes up in early problems. Combinatorics sometimes. I think both of them are important early on, I guess. But not like... Basic math skills is the most important, for sure. Like, I guess discrete math is a good place to start with that. Stuff like proving and stuff like that. Words per minute, around 100. Let's see, is there any question I missed? CP algorithms, that is a good place. CSCS, good place for problems. CSIS, I don't know. If you give up easily, don't. Giving up easily is not a good... I would not recommend that, because the more time you spend on a problem, the more you'll discover about it. Even if you go a bit without getting an idea, that happens all the time. I've gone like sometimes multiple days without getting an idea, and I eventually did solve it. Although I don't recommend that. That's sort of like that's a very heavy investment in a single problem. But you can spend like a bit, even if you don't go that. Like, you can spend a bit of time without getting any ideas before giving up. Templates, GitHub, right here in the description. Do I like Metallica? I'm not like that aware of what that is. So, I mean, maybe, but likely I'm not like passionate about it. You'll find that my knowledge about like stuff in life in general is very lacking. That is unfortunate, but that is how it is right now. Okay, this is where the problems, I guess, step up a little, but they also just kind of don't. Like, I don't know. Somehow this had more solves than these two. So maybe this one's easier. This one's sort of logical, and then they get harder from here. I guess this one did not belong in G. I should probably have put it later. Or people just didn't want to do it, which I can also understand. It's kind of an annoying problem. Where do I stay? Usually in college. I'm at home now because it has AC and my room is hot. So I would prefer to do that. So this is problem D from this mashup. Please make a video on your template. I do plan to do that. That is in the future though. I have been lazy. I have not done that yet. Kickstart. I have not. Because I am... also, I didn't really want to do stuff after 7:43. Oh, it's a rock? Okay, there's probably a good chance that I've heard some of their stuff, if it's that famous then. So, probably. I mean, I'm like, I like different types of rock. It's like pretty cool. So, probably. I also don't really follow creators of music. I just like watch whatever I find that, or listen to whatever I find that's good. Okay, I really don't understand how so many people got this, but this is the next problem. I'm gonna start on this. Palindrome pairs. Okay, you have a list of strings. I'm just gonna skip the story now. You have a list of strings. So for example, you have a list of strings. Yeah, for example, AA, BB, CD, like E or something like that. So you want to figure out the number of pairs of these strings that you can satisfy a certain property with. So a pair would be, for example, like this, or this, or this, or this, or this, or this. These are all the pairs. So you want to figure out the number of pairs that, here's how this works. What you're going to do is, you're going to take the list of characters from here, and take the list of characters from here, and combine them. So for example, you can get something like this. And then what you can do is, you're gonna concatenate the strings, I guess. You can combine the strings together. Then you can rearrange these characters however you want, and you want to rearrange them so that they make a palindrome. For example, here, palindrome is a string that reads the same backwards as forwards. So if you reverse it, it's the same. So you want to rearrange these characters to make a palindrome. So another pair that would work, for example, would be this. You could do BEB, or this, you could do AEA. And as it turns out, these are the only pairs. Nothing works with CD. So the question is, how many pairs works? You have to do it fairly quickly. You have only, you have 100,000 of them. So, something. Okay, right. So at first glance, what does this have to do with Bitwise? And I will answer that question very soon. The first thing to note is, what characterizes a string that can be rearranged into a palindrome? So because we can reorient we can move the characters however we want, really we don't care about the positions of the characters. All we care about is the number of them. So we're interested in, for example, the count of A, the count of B, the count of C, the count of D, etc. Up to Z. And what we want to do with this is what works for a palindrome? So for example, consider when all of the counts are even, right? If we have an even number of A's, we can pair each A up with a corresponding A on the other end. We can do the same for B's. We can stick a B onto one end and we can stick it onto the other end. For C's, we can do the same thing, and for every character we can do that. So if we have an even number of a character, we can pair it up by sticking one on one end and the other on the other end. So even like this, fine. 1 second. Cough is still annoying. My lip is also being weird, but yeah, so we compare these characters however we want. Now the question is, the issue is when we have odd length of stuff. For example, suppose we have CD. That string's just not possible. But if we have something like E, E by itself is a palindrome because it's just a single character. What if we combine it with other stuff? So the key about palindromes is we can put one character in the center. Like for example, we can put this E here. We can put this character in the center and everything would be good. Right. So, but we can only do that with one character. There's only one center. We can't put anything else. We can't put an odd number of characters anywhere else. So if everything, so the condition here is like, if the count of every character is even, then that's good. Or we could have exactly one odd one, so that we can put that odd one in the center, and then everything else will be even, and then everything else can be handled in this way. We stick one on one end and the other on the other. So all even but one odd is also fine. And then the rest is not okay. If we have multiple odd, then that's not possible because we only have one center. That's not what I meant to do. Come on. It's kind of interesting. With the mouse, it defaults to the select. With the tablet, it defaults to draw. So we want to count the number of pairs where either all are even or most are even but one is odd. So the thing about even or odd is like, you do see that this is on a stream about bitwise operations. So somehow we have to involve bits in here. So for example here, even can represent 0, odd can represent 1. That's just how we're going to do this. And then, how is the rest of this going to work? So we can have like a list of bits, for example. We can have a list of bits that represent whether each thing is even or odd. Or we can use a similar trick with like a lot of other problems. We can condense all of these bits into a single bit mask, which is like, it's a single integer. Because again, an integer is represented in binary, so these bits can represent like basically exactly what we want. We can create a 32-bit integer or a 64-bit integer. And what that would do for us is, with this integer, each bit of the integer can represent the state of one character. So bit 0 can represent A, for example. Bit 1 can represent B, and like so on. So we have 26 characters, and we have either 32 or 64 bits. So either of those is fine, as long as we have enough storage space for our characters. So each number can be represented as a bit mask. So the bit is 0 if that number of characters of that character is even, and it's 1 if it's odd. So what is the bit mask of a good string? Well, either it's all 0, or we can have at most one odd. So we can have at most one in the bit mask. The rest cannot be set. So we can have at most one bit that is a 1, and the rest must be 0. So this is how we characterize the answer. Now we have to swing back around to counting the pairs that satisfy it. I don't know what I just did there. Now we have to swing back around to counting the pairs. So let's think about what we would do when we concatenate two strings. Really, all of their characters are added together. So the number of characters in the new string is the number of characters in the first pair plus the number of characters in the second string in the pair. And because we're only interested in even or odd, it's equivalent to doing this like modulo 2. Right? So modulo 2. That is how we add numbers together when we're only concerned with even or odd. We're only concerned with like the parity. It's the last bit. So it's modulo 2. Another way to think about it is, again, bitwise AND with 1, but we don't really care about that right now. So we're doing that for each character. But modulo 2 is not in terms of bitwise, so this doesn't help us. But what is in terms of bitwise is, as it turns out, as I mentioned before, addition modulo 2 is equivalent to XOR. And the reason is just because it gives you the same output. Like if you try the truth table, it will work out. I'm not going to do it here, but it will work out. The XOR is the same as modulo 2. So the combination of two masks is their XOR, because XOR is addition modulo 2, and modulo 2 is what we want because we want even or odd. So rephrasing the problem now, we want the number of pairs such that their XOR satisfies one of these properties. It either has all even or it has at most one odd. Okay, this in itself is not easy to count. Right? But the key here is that this is one possibility. And because there are only 26 characters, this is 26 possibilities. So the total number of different results we can have is at most 27. So what we can do is we can iterate over the specific XOR that we want. For example, maybe we want all zeros. Maybe we want this one to be 1. Maybe we want this one to be 1. Maybe we want this one to be 1. We can iterate over all the possibilities for ones. And if we iterate over the XOR like this, this would tell us exactly the exact number of ways to get each possibility. And then we sum up the ways for each possibility and we're golden. So there are 27 different possibilities. So now we're counting pairs where AI XOR AJ is equal to X, where we're fixing X. We're iterating over X. We're counting pairs where J is less than I. So assume this is a constant. So in this case, this would be constant. So we have C XOR AJ. So another thing is that XOR is its own inverse, because A XOR A is equal to 0. Because all of its bits will cancel out. The zeros will cancel out, the ones will cancel out, everything will be 0. So in terms of like manipulating an equation, what we can do is we can XOR both sides with AJ to make this work. So in this case, we have C XOR AJ XOR AJ is equal to X XOR AJ. But again, this is 0. So we really just want the count of this. The count of J where when it's XOR with X, we can get C. Although this isn't even like the best way to think about it. Another way to think about it is we want the number of pairs where C XOR X is equal to AJ. This is actually better. We want to count the J. We want to count the previous values that are equal to this exact value. So really we want to count the number of this value that we've seen before. So we can create a map that represents the count of each element in the array. And we can reference that map and we can get the number of this element that we've seen before. That is the bulk of it. Yeah. So we just need to count this element now. So after all this, we're converting the elements to the bit masks. Then we're using this formula to count stuff. And we're iterating over X, we're iterating over the bit that's different. There's something else I was going to do here. Forgot what I was going to do something, but I totally forgot what it was. Okay, between this, I'll answer questions now. Facebook Hacker Cup? It's a similar contest to everything else. I don't think it's particularly special. Wait, hang on. I'm seeing the resolution is terrible. Okay, never mind. I'm stuck on 144 on my phone. That's fine. New laptop? Yeah, I have a Mac. Number theory and combinatorics. I will do that later. I have a stream on combinatorics though. Possible to reach 2,000 rating? If you grind enough, I guess. If you grind effectively enough. I don't know what hair falls are. I've heard of split ends, but not hair falls. But like, probably not. My hair is actually just sort of magical. Like it just kind of works. Yeah, my cough is suspiciously similar to hairballs, although there's no like actual hair in it. It's just kind of there. Yeah, mass with only one set bit. Late by a few problems, but not that much. Will I do cook off? Probably not. I'll just finish this stream, and then yeah, I wanna finish this problem. So that is my goal today. You guys again can do cook off if you want, because the stream will be available any amount of time after. Like all of the rest of my streams, their archives are still up. Defaults on 144? Yeah. Yeah, I agree. You have to like manually set it with the advanced, which I don't really understand that design choice. I don't know why they call it advanced, because that's just what it was before. That doesn't really make sense. I'm just trying to scare people off, I guess. Whatever, YouTube is YouTube. A lot of things don't make sense about what they do. Did I leave something here? Okay. Oh, this is... okay. Right, so... let's code this now. Actually, I should not have gotten rid of this yet. So I'll keep that for now. Let's code this. Right, so the first thing we're going to do is we're going to convert all the strings to... we're going to convert all the strings to the bit mask that we want. So for each character in the string, so we're going to do subtract A, and that will map the it will map A to Z to a number between 0 and 25, depending on its position in the alphabet. And then from there, what? And then from there, that will tell us the bit to flip. So we're going to flip the bit that represents 2 to that value. And 2 to the power of that value, we can do it with a bit shift. So mask will be XORed with 2 to that value. And XOR will flip the bit, so it'll become 0 if 1 or 1 if 0. That works for palindromes, because again, we're doing addition mod 2. And XOR is the perfect way to do that. Why is caret XOR encoding and in math? Yeah. And like sometimes exponentiation too. That is kind of annoying. That is how I've seen it sometimes. Caret, the caret, this thing represents exponentiation. Anyway, so we'll do, now we have the mask. So now we want to count the number of each character, or the number of each mask. So we're counting the number of pairs that this contributes to. In this case, we are iterating over the value x. It is either 0 or 2 to the k for k between 0 and 25. Because any of the characters can be odd, it just has to be at most one of them. So in this case, the first thing to do is count of that mask specifically. That's the equal one. Then we're iterating over the bit that we flip. Then we flip that bit. Then we count the new mask. And then we flip it once again so it gets restored to the original one. And there we go, we've counted the pairs. The amount of times I've opened Safari is concerning. Multi-tests. Let's get rid of that. Nope. Wait. Oh god. I screwed up my own... What did I do? I screwed up the directories, I think. Okay, 0. That's not supposed to happen. Alright, our first bug. What is happening there? Oh, because I didn't actually add this into the array. That is something that's important. So 1, 6. Oh yeah, time limit's kind of mean for this one. How many people, actually I'm kind of wondering, how many people have had time limit issues? Is this code legit? No, it's not. If there's legit code that doesn't pass, then I would want to, I don't know what that is. Is there any code that's like actually legit, but... Okay, whatever. Cook-off is going to start. Yeah, again, feel free to do that. This stream archive will be up later. It's sort of unfortunate that the stream timing had to be that, but there's not really much I can do about it. Yeah, update map, you're right. Yeah, I started around 16 or like maybe 15. It's the same sort of range, only off by only a few months difference. How to become this in 2 years? I do have a video on my journey. That is something worth referencing. Use status, yeah, good idea. Not that concerned about it though. Actually, maybe. Yeah, I'll look at it. Problem D. Verdict, time limit exceeded. Are there any legitimate submissions that have not passed? That's not legitimate. Time limit on test 16. Can't read that. Did they eventually pass it though? If they eventually pass it, then that's fine. Okay. By the way, if you guys happen to be watching Cook-Off, it does not hurt to leave the stream tab open in the background. If you do want to contribute, that is something you could potentially do. I would not complain about that. And then you can mute the stream if you want. Legitimate submission is like something that's actually the intended solution. If it's something that's n squared, that's like not supposed to pass, then I would not let that happen. I'll set it to like... The time's kind of not that nice. So I'll set it to 4 seconds. Yeah. Okay, there we go. That should be a bit nicer. Okay, now my submission should be visible. Manager mode is disabled. Let's get to E. E. And then pin that. Cool. That did pin, right? Yes. Okay, now I can erase this. All right, you are given two integers L and R. You want to find, that's way too zoomed in. That's not what I meant to open. Can't quit it. Okay. Quit. Thank you for that. All right, so you have two integers L and R. You want to find the, you want to pick two numbers, A and B, such that they're both within the range. So A is between L and R, and so is B. I guess like, yeah. So A and B are between L and R. And you want to maximize their XOR. Yes, maximize their XOR. By the way, another symbol for XOR is this like plus sign with a circle. I'm going to use caret though because that's how it's designed in code. All right, so the intended solution for this was some ugly bitmask DP. This is not my intended solution though. My intended solution is more logical. So once again, we're going to apply the greedy strategy. What is the highest bit we can make true? What is the highest bit we can make true? And well, how do we answer that? So suppose we have two numbers, like L is equal to, in binary, we'll use 8-bit numbers, so it doesn't really matter that much. And then R is equal to like 0, 0, 1, 0, 1, 0, 0, 1, or something like that, right? So the thing is, for example, these two bits are the same, which means any A and B between L and R are going to have these bits be 0. So they're not going to be part of the XOR. These bits are also the same. These bits are also the same. These bits are also the same. So no matter what, none of these can be set to 1 in the XOR because they're always going to be the same for the two numbers we choose. Now this one is different. So this is the highest bit we can have set to 1. Because they're different, we can select two numbers such that it's 0 in this one and 1 in this one. Now, which two numbers do we select? Well, we can make this 0 and we can make this 1. So for example, in our numbers, we're forced to have these bits be the same. Then we can make this 0, and we can make this 1. Now, what about the next part? What about the rest of them? Well, we want these to be different. We want all of these bits in A to be different from the ones in B. That would maximize the XOR. So in this case, it's 0, 0, 0, 0, 1. And the way to, so can we make all these bits different? And the answer is really yes. We can make them different if we do something like this and this. And this will make all of these bits different. And the reason we can always do this is because this is the highest possible number with this prefix of bits. And so the highest possible number is always going to work because L is like sort of the lower bound. So because we know L has this prefix, we're fine with using the highest possible number because L is guaranteed to be less than or equal to that highest possible number. And therefore it's going to be part of the range. And it's less than or equal to that because we know that it's the highest possible number with that prefix. So there's no way to get higher than that. And similarly, we're using the lowest possible number for this prefix of R so that r is guaranteed to be greater than or equal to that, and it'll always be within the range. So that lets us have as many ones as possible. These bits have to be the same because they're the same in L and R, and everything before it is also the same. Which means there is no choice of A. There's no choice of A or B that doesn't have this as the prefix, because every number between L and R has that as the prefix. There's no way around that. Okay, so as it turns out, the first point where they're different determines the rest of the answer. For the first point where they're different, we can make that different bit 1 using this, by just making them different. And as it turns out, by using all 1s in A and all 0s in B, the highest and lowest possible numbers respectively, we can make everything else 1s as well. So really, the only hard part of this problem now is finding the first bit where they're different. There are so many ways you can do this. You can just iterate through the bits directly. A fancy flex trick you can use is you take their XOR, and you just take the XOR of L and R. And for all bits where they're the same, this XOR will be 0. So L XOR R in this case will be 0, 0, 0, 0, 1, 1, 0, 1. And the reasoning here is that all these are 0 because they're all the same, and then this one is a 1 because it's different. Now we're looking for the first 1 that we can have, which is the most significant bit of the XOR, which we can find in O of 1 using the formula I described in the previous problem. For example, with long, it would be 63 minus the number of leading zeros. Now the only caveat is that the function for counting leading zeros will crash if it's past 0 as an argument, because there's like no real way to define the number of leading zeros if you have 0. So if you pass in 0 for this function, it will crash. So mathematically, this will always work, but within code, because there's this special case, you have to have a special case for when the XOR is 0, which implies that L is equal to R. So if L is equal to R, make a special case. Otherwise, the answer is you can have everything. You can have every bit, including this one and lower. So to make this work, we'd read in the numbers. If L is equal to R, just print 0. Otherwise, we take the XOR, and the most significant bit is 63 minus the leading zeros, specifically the long of X. And then, yeah, so the answer here would be 2 times this, because essentially, because we can get this bit, the number we're getting is like, this would be 2 to the most significant bit would be this. But what we really want is all of this. So one way we can do that is we can multiply this by 2 to get 1, 0, 0, 0, 0, and then we subtract 1 from it so that this becomes a 0, everything else is set to 1, and that's how that works. So that's where this comes from. Actually, that's wrong. Why is that wrong? Something is up with that. Wait, 2 times MSB minus 1. This should be fine. Oh, right. It should be 2 to the MSB. Whoops. Not the MSB, not the most significant bit itself. That doesn't really make sense. Safari, I swear to God. Also notice that the samples here are always a power of 2 minus 1. That's another hint for the answer. So yeah, this should be 2 to the power of the MSB, not the MSB itself. There we go. Special case right here, make sure it doesn't crash. Yeah. So this is a 1700 rated problem, and it has this for a solution. You could theoretically compress this into a one-liner. So yeah, that is very cool. What? Okay, that's weird. This could be overflow. Oh yeah. A mistake here. This should be okay, yeah. This is a good thing to work on. That if you do a shift, this is just an integer, so it will shift this integer. That is a mistake. This will shift this integer. It will try and shift it into like 2 to the 60th, for example. But an integer is not capable of handling 2 to the 60th, so this 1 is too small. So instead of shifting an integer, we need to force this to be a long, and the way to do that is to explicitly pass a long as the thing that's being shifted. So that is a mistake. It is a good thing that I made that, so you guys can be aware of that. I do not play CSGO. Okay, I think digit DP was the right word. I didn't really mean bitmass DP. So you probably did what I was thinking of. It would be digit DP based on like, I'm not going to explain digit DP here because it's complicated, but it would also work for this problem. All right. This problem will take a lot longer to explain than it will to code. So I guess let's get into that. Alright, we have Apollo versus Pan. Only if you know that... No, okay, I'm skipping the story. You have an array, find this sum. That's what the problem is. You have an array of large length, you want to find this sum. So, let me write out this sum in detail. So it is the sum from I equals 1 to n of the sum for j equals 1 to n of the sum from k equals 1 to n of this quantity xi bitwise and xj times xj bitwise or xk. Current problem. Yeah, good. I always forget to do that. I wish... Actually, no. There's no way to make that automatic. Yeah, I don't think that's happening. How many times I have to delete that message? Good catch, good catch. So yeah, this is problem F. Right. This problem is an ordeal. So, first of all, we can rearrange the sum however we want. And the reason we can rearrange this is because I'm trying to think of how best to represent this. One of the best ways is like, I guess I'll do it visually. So imagine n equals 2. Now imagine like you have this 3D array. Can I draw a 3D array? Yeah, I don't think this is a good idea. Essentially, you're summing over all values of a cube. but I'm going to explain it a different way. Basically, wrap this whole thing in a function that's like f of I, j, and k. Then as long as we get every triple I, j, and k, where I is between 1 and n, and j is between 1 and n, and k is between 1 and n, and we get all of these triples, as long as we get all these values somehow, sum is commutative, so we can swap the order and it doesn't matter. So really, as long as we cover all of these tuples of values, it doesn't matter the order in which we do the sum. And because everything is from 1 to n no matter what, with any order of summation, it will work. So we're allowed to swap these, because we'll get everything no matter what. And so, which one do we swap? Well, I sort of hinted at that already, but the strategy here is we're going to do the outer sum. We're going to iterate over the outer sum. So for example, we're going to iterate I from 1 to n. Now, what that means is we need to compute this inner part in a fast amount of time. So we know what I is. So xi is essentially a constant. So replace it with like c or something. And then we need to compute this inner part with this part held constant in a quick amount of time. But this isn't easy with I. But notice that j is the most involved here. J is part of both of the parts of the sum. So it's probably a good idea to try working with that. So we'll move j to the outside. Of this function, xi and xj times xj or xk. So again, we are holding j constant. We are iterating over j. Now we need to compute this inner part in less than O of n, because there are O of n values of j. So because we're iterating over j, we are holding j constant. That means that both values of xj is just some value c. It is some constant. It does not change. Right. Okay. So we need to mess with this sum a bit more now. Summing these multiples is not going to work. But notice that this part depends only on I, and this part depends only on k. So really this can be represented as some sort of f of I, and this can be represented as some sort of f of k. And thinking about it this way might make it easier to think about these rearrangements that we're going to do, because we're going to mess with the sum a bit more. We have f of I times f of k. Now notice that within this sum, f of I is a constant, because it's like it just is. When we change k, f of I does not change. So f of I is going to be multiplied by every part of this summation, which means that it doesn't change anything if we compute the summation independently and then shouldn't use, okay, fine. I will make that g. Sure. Yeah, it doesn't really matter. The point is, it's just some function, but sure. Like, the point is we're summing this function over. This should be an I. So, like, yeah, f of I is constant here. So it does not matter, like, within the summation, because the summation only considers k. So we can drag it out, and everything will be the same. So in particular, we will do this. I equals 1 n of f of I. Why do my eyes look like j's? That's kind of a curse. Times this stuff. But at the same time now, considering this, actually this is probably enough, but just to take it a step further, considering this summation now, this part doesn't depend on I. It only depends on some k. All right, so for each I, this part is going to evaluate to the same thing every time because it doesn't depend on I. So within the summation of this is basically constant. So once again, we can pull it out because it is constant within this summation over I. So really now we have two independent sums. The sum from k equals 1 to n of g of k times the sum from I equals 1 to n of f of I. So now we've reduced it to computing these two things individually, and only then will we multiply them together, and then we will consider this over all j. So let's just figure out how to do one of these parts. We need to compute this sum, the sum from I equals 1 to n of ai bitwise ANDed with some constant. Now, once again, we are going to use the idea that bits are independent, and this is sort of very important here. Bits are independent. So let's consider the bits of C. For example, I feel like I'm biased towards zeros, so I'll try and make that even. So we're considering the bits of C. Recall or just think about the rules of bitwise AND. If this is 0, if this bit of C is 0, everything is going to be 0, because 0 and anything is 0. 0 destroys, 0 is a destroyer in AND. And let's consider some AI as well. So for example, it doesn't really matter. Right, so this is all 0. And then when we bitwise AND with 1, it becomes unchanged. Because 1 and 1 is 1, 0 and 1 is 0. So 1's not going to change anything from the bitwise AND. Right? So for each bit, because we're counting the summation, we want to count the number of times this bit is set, and then we'll multiply that by 2 to the value of this bit times the count, the number of times it's set. So for example, this would be, if we figure out this bit is set k times within the total array, or within the total summation, this would be 2 to the 6th times k. That would be its total contribution. Right. So we know when the bit of C is 0, everything is automatically 0. So k is automatically 0. But for the ones that's unchanged, essentially now we're reducing it to counting the number of times in AI that this bit is 1. So we're counting the number of ones in AI. So we're counting the number of ones that this bit has throughout A. Oh, Jesus. Okay, 1 second. I need to move this laptop. It's almost killed it. Yeah, let me get that out of here. Okay, gonna try and not kick that again. That could have been very bad. Well, that just happened behind the scenes, but I just almost destroyed my old laptop. So let's not do that. So we're counting the number of ones throughout A. So this is independent, again, of whatever C is, which means we can pre-compute this. We can pre-compute for each bit, how many ones does it have in A? And that's the answer. So we're representing this as a new summation. we're iterating over the bit. So for example, the bit b is equal to 0 up to like whatever the number is, like 31, for example, or no, 2 to the 60th. So the number's up to 2 to the 60th, so we have to iterate up to 60. Be very careful with overflow here, by the way. So it's like 2 to the b times c1. Technically, this can be up to 59. Doesn't really matter. But 2 to the b times the number of ones we have. And again, we do this casework. If this is 0, the answer is 0 automatically. If it's 1, we need the number of ones of that bit in the array. The other part is bitwise OR. It's almost the exact same. But the difference here is if this is 1, then it's always 1. Because that's how OR works. And otherwise, it's unchanged. So the casework changes a bit, but the overall answer is similar. So backtracking now, once we have this, we get this summation. We also get the other summation, then we multiply this together, and for each value of j, we're going to do that. So yeah, that's how this problem works. It's a lot of involvement. But ultimately, the solution ends up being simple. So let's just first read in the array. So we're going to create a count. And so we're counting for each bit. How often is this bit 1? For example, here we're going to iterate the bit over 1 to 60. If this bit is set, the way to count if this bit is set is, for example, we would right shift by this bit, and we bitwise AND it with 1. Then we would increment the count of that bit. Note that you can directly do like count b plus equals this, but for the sake of explaining this, I think this makes more sense logically. It's just if this bit is set, increment the count. Right. Now we're going to do this part. So for j equals 0, j is less than n, j plus plus. Hello, Aaron. How are you? So for j equals 0, j up to n, j plus plus. We're going to do the AND part. So for example, this is the value of the AND. Also, the mod is 10 to the 9th plus 7. Be careful with modding here because the time limit's not so nice. I might change the time limit for this one too. So we're iterating over each bit. So first of all, the value of c is simply aj. So if this bit is set in C, we're counting the bitwise and also the bitwise OR. This is 2 to the b. Also mod because we have to do that, but we just need this value, so we might as well do it at the beginning. So if this bit is set, how does it contribute to the AND? Well, with the AND val, we add 2 to the b times the number of ones, which is count b. And then if this bit is 1, then automatically we get all of the ones because the bit is 1 in the OR, so we just add n here. Otherwise, this bit is not set. So in this case, for symbolicness, we get nothing here. This line is useless. I'm going to delete it, but the point is... Actually, I might as well not delete it, just for the sake of showing that this does nothing. Because here we do consider this, but because the bit is 0 here, everything and that is going to be 0. And for the OR, we add the count. This is the casework we did earlier. And then we add to the answer that. And we're done. Plugging in formulas, basically. That's what the code is. Multi-tests. I always hit Option C instead of Control C. That's kind of confusing because it just inserts some random character. Like here, I would just put that in instead of actually stopping the program. That is very slightly off. Oh yeah, I need to do, wait, do I? Wait, what? Right, 1LL. Once again, same mistake. I haven't done bit shifts in a while, that's why. There we go. This might TLE. If so, I'll make the modding a bit smarter. But yeah. Seems fine. Okay. Yeah, time limit is not even close. Okay. Try gvim. This isn't Notepad++, it's something called TextMate, but yeah, I don't know. I'm fine with my editor right now. Other people have recommended me other things, but I'm fine with this. How do I practice? Usually I pick a difficulty, like sometimes I'm doing 2800, sometimes I'm doing 3000, stuff like that. Another way is doing virtuals. I think virtuals are also helpful because they let you get used to contest environments. But they help more if you're able to solve many problems. If you're only able to solve a few, you might as well just practice a certain difficulty. Okay. Some other things. Yeah, the other, I do like the theme that this has. It's sort of satisfying to use. Cool, different countries, yeah. That is nice. I'm from the US, by the way. In case anyone didn't know that. Just saying. Yeah. Freshman, first year in college. Studying computer science. Well, trying. It is sort of... There is an asterisk there, but I will eventually be studying computer science. Am I focusing on ICPC? Sort of. Not really, but that is something I will be doing. I'm not like trying super hard trying ICPC, but it is something I'll be doing. I think motivation is pretty low at my university, like overall. So I don't know how that's gonna go. Okay. We'll update the problem once again. Although I did hear someone's... Okay, actually, wait. There should be an option, right? Yeah, never mind. What's problem G? Did I struggle when I started? I mean, somewhat. I got totally flattened by used to go silver. That is the struggle I had. Although I sort of had like the logic skills from, I guess, school and stuff like that already. I didn't really do math competitions, but my school was pretty good at teaching like how to actually problem solve instead of just telling you what to think. So that was pretty nice. Is it entirely computer science? Yeah, I'm not doing an engineering part. Any reason why I don't use other text editors? I just like this one. Sublime I know has problems with infinite loops, and I don't really want to like... If I try to fix it and then I fail to fix it, it will screw me over at the worst time. Really, I don't want editors that control my terminal because I want to be sure that if I'm doing something dumb with my code, it's my fault and not my editor's. So if it is the editor's problem, I do not want that potential to happen. Because I know many editors do have issues that people have had specifically with those. What happened to the old laptop? Let me see if this shows well. Basically, I don't think this is that good of an angle. Let me see if I can. Okay, hang on. If I change this midstream, is it fine? Yeah, I can do this. So basically, like this part right here. See if I can get a good angle on it. It's just sort of broken. Like you see how it's sort of detached on the side here, and then when I close it. The further I close it, the more it sort of breaks. Hang on, I'm not getting the right angle here. And then eventually I'm figuring that if I did try to close it, it would just totally like come off or something like that. So I don't want to mess with it. We are eventually going to get it fixed, but I can't really take it to college because I can't like do anything with it. So that is why I got a new laptop for college. I can finally show that now because I have another camera to do that from. That didn't mess with the mic, right? It's still, yeah, it's the same audio settings. Okay. Does coding in Mac differ a lot from Windows? No, not really. Because I used the Linux-style terminal anyway. So this is basically the exact same stuff, actually. The only difference is instead of ./a, I have to do a ./a out here. But it barely makes a difference. And like the text there is a bit different, but it functions the same as Nova++, basically. So it's like fine. The only thing I do miss is Control D, which used to duplicate a line. That doesn't exist on this editor. But other than that, like a lot of stuff is just fine. It's not. I'm not feeling the difference that much. All the hotkeys are different, and it sort of took a while to get used to. But after that, it's just natural. It really doesn't matter what kind of OS you have or stuff like that. I mean, maybe for other development, I know a lot of people prefer Linux. I have not experienced that myself, but I'm sure at some point I will realize the difference. I do not play guitar, like, my parents just sort of bought me this, and then I, like, used it for a class. But I never really got into it that much. Any guitar stuff coming up? I do not have any class on that, so unfortunately, no. Yeah, feel free to have your opinion on OS. Sure. Okay, Bitwise formula. Right, so in essence, this problem asks you to simulate kind of a program where you're setting a bunch of variables. And all these variables have m bits, so they're m bit numbers, and you have n of them. Right, so like just for example, look at this sample to see what you really have to do. You have to do A gets a value, B gets a value, and C gets this question mark. And what you have to do is you have to choose the value of this question mark so that you have two goals. The first goal is to minimize the sum of all the variables that exist. So you minimize A plus B plus C, and you would choose this question mark accordingly. The other part is you want to choose the question mark to maximize it. So this part would be the question mark that minimizes. This would be the one that maximizes. And so within these programs, you have to do this for each of them. Right, so we gotta do this, right? So in what way are we going to do this? Well, repeated again. I changed that. Repeated again and again. Very, very common idea. Bits are independent. This is bitwise AND, this is bitwise OR, this is bitwise XOR. We're going to independently minimize the sum that each bit layer will contribute. All right, so how do we do that? Well, because we're minimizing each bit layer independently, because all the bits are independent, for each bit layer in the question mark variable, and there is only one question mark, there is only one variable that's like actually a variable. The others are all fixed or some function of the fixed numbers. So because we're only focusing on one bit, there are only two possibilities for the question mark in this bit, 0 or 1. So for this bit, we can try both possibilities. We can ask, does the question mark have a 0 in this bit, or does it have a 1? And in either case, does it have a 0 or does it have a 1? We try both. We see which one gives us the minimum. We see which one gives us the maximum. We do what we want. There are several ways to get the same score. Find the minimum number that can be chosen. So in this case, these will both be 0. Right, so let's go ahead and do this thing. Ow, okay. Okay. So how do we implement this? I'm assuming that this has so few solves only because it was actually a pain to implement. For example, this has 4 solves, which is sort of expected. And the next one has much more. But yeah, so how do we implement this? Again, we're going to focus on each bit level independently. So the way I'm thinking about implementing this is, I feel like also I could have done some drawings for that. I don't know why I didn't actually. The idea is pretty simple. We're considering each bit level independently. For each bit in the question mark, we're asking, like, for example, we try 0 and 1 in this. We pick the best. We try 0 and 1 in this bit. We try 0 and 1 in this bit, all independently. Okay, so the way I'm going to sort of compute this is I'm going to represent it as how computers represent operations. We're going to build a tree out of it. So, well, it's not necessarily a tree. It's more like a directed graph, per se. So for example, here, this would be, let's see, okay. So we have A in the bottom, which is a constant. We have B in the bottom, which is a constant. We have question mark, and then we have C, which depends on these two. That's the first sample. In the second sample, we have A, I'm losing my tabs. We have question mark, we have A, we have BB, we have CX, which depends on these two. We have D, which depends on this. This is kind of a mess. And then we have E, which depends on these two. This is like very much a mess. But another thing that's important is that when we define C, we can only depend on variables that exist before. So no variable will depend on a future variable. And that means that like this sort of directed graph of dependencies is actually acyclic. There are not going to be cycles in it. And what that means is when we compute a value, we can be certain that value will only depend on previous values. So the reason why that's nice is wait, let's see. The reason why that's nice is because it is. Like, okay. Hang on. The reason why that's nice is because we can sort of do it like, it's sort of like a DP fashion, but it's more like memoization. Really, when we compute E, we're going to rely on the values of D and BB. Actually, let me find a better example. So for example, just like A is equal to 1, B is equal to A, XOR A, and C is equal to B, XOR B, or something like that. Right, so here it would be dumb to compute A twice. So really, once we compute the value for A once, we're going to stash it, we're going to memoize it, and then we save that value. So that every value is only computed at most once. That's the whole point. We're going to use memoization of the variables. So here, same thing. We will store the value for B once. We will refer to it instead of recomputing B every time afterwards. So now, implementation. What I'm going to do is I'm going to assign each variable sort of a number. Like, for example, we have A, B, question mark, C. I guess question mark will be 0. So we'll think of it like question mark, A, B, C. So then, strings are at most length 10. Right, so this will depend on nothing. Implementation-wise, A is equal to 101, B is equal to 011, and C is equal to some F of B in question mark. So the dependency of A will be, I'll just put the direct string on the first one, and then the second one will be the string -1. So that if the second value is -1, we know that A is equal to a constant, or it's equal to the question mark. So also note that there are no variable assignments here. I can't, for example, set B equals A. In this format, this will only be a binary string, which is convenient for this representation. It means that if it's -1, it's guaranteed that this is a constant value, and therefore we're referring to the binary like bit of this value for the first one. So this one, for example, would be something like 011, -1. And then this depends on the value B and the value question mark. So we can refer to these dependencies when we're computing a value. This is all we need to store from the input. We're storing what each thing depends on. So I guess, like, yeah. All right, so first thing we're going to do, we're going to store the dependencies. We have up to 5,000 of these. And we have n variables. Okay, so now we need to read a list of strings in where we don't exactly know how many strings we have. One way to do that is I usually use a string stream for this. Let's see, which one would I use? So there's I string stream and O string stream. I kind of forget what each of them does. I string stream is like, I definitely forgot which one this is. So it's like you read into it. Right, okay. Yes, this is the right one. Yeah, with getLine. So first thing is we're using getLine, which is a function that will literally just get the whole line. So it'll search until you get a new line. So we'll get this whole line, for example, like this. And then what we're going to do is we're going to create a string stream. And what this does is essentially, you know how like cin basically will cin basically like is a stream. It will just like separate stuff by spaces, and then it will feed you the words it parses one by one, kind of. And that's what this thing is doing. You give it a string, it will separate it by spaces, and it will feed you the words. So it will return false or some null value if it doesn't read into anything. And it will return something that's true. It will return itself, which is evaluated to true, if like logical true is anything that's non-zero. So it will return something that's evaluated to true if it does read it in. So we can do while we read it in, and this will work as expected. While we read into something, it will be into t. So we're gonna store the whole line, and then line.pushback t. Now we have a list of space-separated arguments of this string. This will work with like anything that's like line separated. So now we have two cases. If we only have 3 arguments, then we know it's the first type. So we also need we also need a map from strings to integers. So because everything is integers, we can use like indices. So for example, this is C would be index 2, B would be index 1, A would be index 0. It's just the strings in the order that they're referenced. So val of line 0, which is the first string, is equal to I. Then dependency of I is equal to, again, the binary string itself will be what it's dependent on, and then the other thing will be the string -1. Otherwise, it's of length 5. So the dependency of I is equal to line 2 and line 4. And then the operation is like this. We also have to store the operation so we make sure we're doing it right. So this will this will depend on the question mark and the B. Actually, let's see. Dependency of question mark is equal to 0. Then this will be I plus 1. Everything will be I plus 1 here. I don't need to do that. You can make question mark n. Might actually be easier. Whatever, doesn't matter that much. Peter, huh? Yeah. All right, now we have to do the computation part. And the way to do this computation part is, once again, we're going to iterate over each bit. String I'm going to keep the strings at the minimum and the maximum. So for each bit, up to m, I plus plus, I should read m as a variable. So these are going to be global just because I'm lazy. So the first global variable is going to be the setting of the question mark. Is this 0 or 1? This is like the question mark value. And the other one is the bit itself, just the bit that we're working with. So bit is equal to I. So we're going to count the total number of ones we get if the question mark value is set to 0 or if it's set to 1. Count 0. Right. So within this count, we're simply going to set qval is equal to val. And then we're looking for the sum of all variable values. So we're going to count for each variable, is it 1 or 0 at this bit. So like to plus equals get I. Turn to. Right, so now we're defining this recursive function get. We're also going to reset our memoization. Get LV. Okay, so if v is equal to 0, return qval. This is the index of the value. So if v is equal to 0, we're asking about the question mark, so return that. Right. So b is equal to 0, return qval. Otherwise, it has two cases. Either it is a constant value, or it is a value that depends on two other values. So if dependence v.second is equal to the string -1, then return dependence v.first. That is the binary string, like that is, it's set to constant. That at the index of bit, and that -0, so we convert it to 0 or 1, minus the character 0. Because it's currently a character, we want it to be the value 0 or 1. Now this indexing looks slightly stupid, but it should work. Right, so now we're looking for the value that the left thing depends on. So we're looking for the value of, like, the index of the left and the right. Okay. So if op v is equal to XOR, return if mem v is not equal to -1, return memoization. Mem v is equal to left, get left, XOR, get right. We do two similar things except with or and. If it's none of these, then we have a problem. So we just crash it, because that shouldn't happen. But yeah, that should do it. So now we assign these. If C0 So if C0 is less than or equal to C1, then we want the minimum value to be 0. We want it to be as small as possible. So if C0 is greater than or equal to C1, then we can set it to maximum. And the reason we're including equal is, again, because if they're both possible, we want it to be as small as possible. Oh, it should be val, not dependencies. Cool, let's see how this works. Segmentation fault, okay. That's sort of expected, I guess. Is it because we're using multi-tests? Indeed, it could be. Let's try that again. Segmentation fault again, okay. Alright, here we read in N and M. So, val of line, alright, so, let's make sure we're reading this right. What? Okay, so it's not reading that right. I feel like I'm messing something up then. Right. Right. Forgot this is something also that CM will not read in the end new line, so the first get line will actually like not be what you want. So you have to do like cn.ignore or something, and that will make it so it will ignore the current new line. I don't exactly know what cn.ignore was, but it like that will fix the problem. I'm always sleepy. That's not something that can be avoided. Should both be 0. Okay. Could be wrong, I don't care. We'll submit. Wow, that was actually very close. What the hell? Why did that take so long? I feel like my original submission to this was faster. Well, whatever. Wait, actually, how slow? Okay, this is actually like very slow. I'm very surprised that it took that long, but any verdict? Yeah, some TLEs. Okay, people had. Wait, how did this guy solve it so quickly? Oh, it might have been like iterative. Yeah, you can do it iteratively too, either way. Guess you could do things very quickly. Typing speed, like around 100 words per minute, sort of depends on various factors. Depends on whether I know what I'm doing. If I'm reading off the screen, like in a typing test, then it will be considerably worse. Well, that's natural for everyone. I make a lot of typos too. Especially with code, where you use a variety of different weird characters. Okay, this was my example of bitmask DP, I guess. So there are n dishes. He knows he needs exactly m dishes. With that, he does not want to order the same dish twice, so you want a distinct set of dishes. Oh, it's a parrot. Okay, that sort of changes a lot. Notice that the ith dish gives him AI units of satisfaction, but some dishes don't go well together. Some dishes go very well together. So if you eat dish S, X exactly before Y, your satisfaction level will raise by C. Of course, you want to get maximum satisfaction, so help him with that. Right. So essentially, you're going to eat some dishes in some order. You want exactly M of those dishes. And there's a special rule where if you eat like a certain pair of consecutive dishes, you might get a bonus. I'm going to find the maximum value you can get. So within like a DP state, because this is specifically chosen for bitmass DP, the stuff that matters is first the dishes we've already eaten, because the question we're going to ask is what's like important? What will affect the choices that we can make? Here, the choices that we can make depend on two things. It depends on if we've eaten this dish before. We cannot eat the same dish twice, so it depend on if we've eaten this dish before. And it also depends on the previous dish we ate, because the previous dish affects how much satisfaction we can get. No other information is important because nothing else will affect the decisions we make. Everything else only contributes to the satisfaction level. We don't care about the order of the previous ones. So the state here is the set of dishes we've eaten and the previous dish we just ate. So in this instance, we can store like the value we get from eating dish A right after dish B. Or like that. And it defaults to 0 in case we don't get anything. So defaulting to 0 is good. Global variables will default to 0. So let's read in the values. Did I miss some chat, by the way? Guitar, no. No. I don't even know how to play guitar anymore, to be honest. I don't really like participate that much in the class, admittedly. So we're going to zero index x and y, combo x, y is equal to c. So now the DP is, there are 2 to the 18 possibilities. Each possibility, I guess I'll write this out explicitly. So max satisfaction, God, handwriting, I'm sorry, that's horrible. The maximum satisfaction where with the mask of dishes eaten, and we ate x previously. So the way bitmass DP would work was normally we would have DP where we have a state value for representing each dish. So for example, like DP of A, B, C, right? And this to represent if we've eaten dish 0, if we've eaten dish 1, etc. But we don't do that. We instead compress it into a single number, and the bit of that number represents whether we've eaten the dish or not. That is what bitmass DP is. It's just an efficient way of representing a list of bits as part of a state. So the transition is choose a new dish to eat. And then when we choose a new dish, we set that bit, and x becomes y, of course, because that's the new dish we ate, and then add satisfaction. So choosing a new dish will only increase mask, which means that we'll iterate from mask from smallest to largest, from 0 to 2 to the n minus 1. And that'll be fine because larger states will only depend on smaller states, because adding a dish always increases the value. So this will be, for example, 18. So we're going to set all dpij initially to some negative infinity, like negative 1e17. And then dp of 0, having eaten what does that sound? Okay, it sounded like an alarm for a second. That would have been bad. Okay, so what I'm going to do is I'm going to represent a special dish 18, which represents not having eaten anything before. Because initially we don't eat anything, so we need to make sure we don't actually like get a combo that we don't deserve. Another way you can handle that is you can, instead of starting with 0, you can start with, like, for example, the initial state is having eaten a particular dish, and then you fix the dish, and then that's the state you start off with. That's another way to do it. So then, alright, so actually this is the same thing. Right, so I'll just comment this stuff. And this is the new dish we will eat. Then what happens? So actually the first thing to check is that this must actually be part of the mask. So we can only have previously eaten a dish if we've actually eaten that dish. So the first thing to check is if I and j and 1. If the jth bit of I is set, then we know that we've eaten that dish. I'm struggling with this. What? Hit tab. Why does this not work? This usually does work. I don't know what's wrong with that. So then now we're going to check, as long as the new bit we do is, it has to not have been eaten already, because if we eat a dish we've already eaten, that violates the rules. So if not the value of I shift k and 1, then now we can eat this. So the new mask is I, and we can use bitwise or XOR or plus, any of them work. But the point is we're adding on the bit that we have not eaten yet. So this is the new mask that we would get because now we've eaten k. So the previous value is dp of ij plus ak. And then we also get the transition of the combination of wait. Okay, actually this doesn't work. I'm gonna do the other thing. Yeah, this doesn't really work. Okay, so I'm gonna set this to 1 now, because 0 is a useless state. 0 doesn't actually make sense. Yeah, this is sort of just confusing myself. So we also get the value of, we just ate k, and now we just ate j, and now we just ate k. So if we get any bonus from eating j and k together, this is when we get it. So then dp new mask. The new state is the new mask, and k is the previous one we ate. So we maximize that. The term for that is relaxing. We relax the new dp state. with this value. I don't know why it's called relax, but that's what it is. Okay, so first, now we're going to iterate over the first dish that we eat. So for example here, dp of 2 to the I, and let's see, the previous dish should be I, would be AI. This would be the state of we initially, this is the first dish we eat. So the mask would be simply this dish. The value here, previous dish should be this dish, and the value we get is this. Now we restore the answer. We need to find the maximum satisfaction, and the way to do that is we're considering only bit masks that have exactly k dishes. So for I equals 0, I is less than 2 to the n, I plus plus. If we have exactly m bits, we can do that with pop count. I is equal to m. We can check this. It's not strictly necessary because if this value doesn't exist, it's going to be like negative infinity anyway. We might as well check this just in case. Ants is maximized with ants and dpij. So this first part is initialize everything to negative infinity, initialize the initial values, do the dp, and then look over the masks that have m bits set and find the best one from that. We get 3. We get 12. See if it works. I doubt it, but who knows. There's like a fairly decent chance. There we go. Oh, this stream is still here, right? Okay. Cool. That is bitmask DP. There's one other instance of bitmask DP, though it's less traditional, and the DP is just sort of part of it. I think I forgot to update the problem. Yeah, I did. Okay, cool. I will do that next time. Yeah, I'm very good at this, huh? It's been a while since I've done these streams. But yeah, I am going to continue them in the future, by the way. Current problem is I. I'm going to pin that one. Okay, we have 5 left. We can look at chat somewhere. Yeah, Kickstart apparently use bitmask DP. That's cool. How to jump off to harder problems. I mean, yeah. It's always just practicing stuff that's hard for you. Practice the stuff that's outside of your comfort zone because it's going to be harder to learn it if you're just doing the stuff you already know how to do. Just jump right into it and see what you can, and if you can't, then you can learn from not being able to solve it. You can figure out what went wrong and why you didn't see what the solution was. It's always just learning, practicing, making mistakes, and analyzing them. It's very important to figure out what went wrong with what you're doing. My classmates similar to me? No, not at least not in college. Mostly, at least in terms of competitive programming. People do other types of programming too. And they're certainly better than me in that. Frequency, that is a good point. Did I say infrequent? I said inconsistent, I never said infrequent. So the streams probably will happen quite often. Like I will probably do one next week. Although I have still not fixed the new polling option, so we're probably going to have to do comments again. Oh, this is the other bitmass DP one. Okay, yeah, this is indeed a troll problem. How many hours do you practice when I was a beginner? A lot. That period of being a beginner was when I practiced the most. It was like very much. It was like 2 to like 7 hours a day, and even more on weekends. Just whenever I had free time, basically, that was what I put into it. Sticking with the same problem. As long as you're getting stuff on it, if you spend like a considerable amount of time with no new ideas, like maybe 30 minutes, if you try a problem and you keep thinking about it and you keep getting ideas for it, then there's no reason to stop, because even if you're not making progress, you're still thinking about it. And you're seeing what works and what doesn't work. But if you got nothing, like absolutely nothing that has a chance of working, then that would be considered like being stuck. And after a while of that, you could finish it off. You could stop the problem, or read its editorial and figure out some stuff from that. All right, 505. I don't know where that comes from. Binary matrix is called good if every even length square submatrix has an odd number of ones. Given a binary matrix A consisting of n rows and m columns, determine the minimum number of cells you need to change to make it good, or report that there is no way to make it good at all. All the terms above have their usual meanings. Okay, nice. I like that statement. First line of input contains 2 integers and whatever. If you do have more ideas to try them. That's fine. Okay. I know the solution to this, so I'm just gonna go over it. The idea for this is you just gotta like, let's see. How do I explain this generally? So the idea for this is an even like square submatrix represents 2, represents 4, represents 6, etc. But notice that 4 is 2 times 2. So an even like submatrix of size 4 will contain 2 of them that are of size 2. So this overall thing is 4 times 4. But within this, this specific one is 2 times 2. And so is this one, and so is this one, and so is this one. So note that because all of these independent ones have to be odd, within this 4 times 4 one, we have the sum of 4 odd numbers, which is even, which is not possible. So any 4 times 4 square cannot exist, because it is the sum of 4 2 times 2 squares, all of which also have to be odd. And so because they're all odd, this one is even, it's not possible. So if there's any 4 times 4 square, it's automatically not possible. Otherwise, it's basically always possible. You can show that. Otherwise, the only submatrices you care about are the 2 times 2 ones. So first note that the number of rows is less than or equal to the number of columns. So n is less than or equal to m. So if n is greater than or equal to 4, then you have a 4 times 4 one, and therefore impossible. Right, so now n is less than or equal to 3. Because if n is greater than or equal to 4, immediately we can stop. But now n is less than or equal to 3. So we have a up to 3 row matrix, and we want to make sure that every submatrix of size 2 has an odd number of ones. So it's always possible to do this. One way we can do this is, for example, we can use a pattern like this, etc. And so this works, everything works. Yeah, so that's one thing that is possible. But of course there are other ways to do it. Like there are other constructions that work. Like for example, another way to do it is, I think this would work. Something like this would work too. Like there are a lot of different ways you can do it. Another one is, for example, this. I do not recommend enumerating the patterns. That's a dumb strategy. Don't do that. Because like for example, you can have stuff like this, and I think this would also work. Like the point is there are a lot of different ways to have a working solution. So don't try and bother with stuff like that. Instead, let's just not look at the structure at all. We're just going to bash it out. And the way we bash it out is bitmask DP. Often people call this like broken profile or something like that. I think people have called it gap DP. I don't remember what exactly that's called, but people have used some weird names. So like, for example, here, off-campus robbery with a weapon. Awesome. So like, for example, here, one of the states would be our current column. And another thing we could do is, suppose we've built like the first k columns of the matrix. So what that means is that everything within these k columns works out. All of these, that drawing doesn't make sense. But all of these squares are valid as we want them to be. And we have some values here, for example. So we know that all of the squares to the left of this are going to work out. The only squares that we don't know that are worked out are the ones that involve half of this column and all the ones to the right. So we know that everything else is satisfied. So all of the numbers over here, we don't care about them because we already know they're satisfied. The only numbers we care about are the ones that are on the rightmost column, because those are the ones that are going to affect our future. So if we were to have a state, this rightmost column must be part of it. Then the transition would be, we put down a whole new column at once. So for example, something like this. Then this would be satisfied, this would be satisfied. Our new state is something like this, and this is our new rightmost column. So the DP state here is the column and the mask representing the rightmost column. Note that this is easily representable as a mask because it's just a bunch of bits, specifically up to 3 bits. The total number of states, thus, is they're up to m columns. They're up to m columns, where m is like 10 to the 6th over 3, and the mask is 2 to the 3rd. Right, so let us go ahead. So how do we do this? I'm ignoring what's going on in chat right now. So how do we do this? I mean, this is it. Like, transition is put down a new column. Or is this sadly not out of tradition, though I very much wish it was. Okay. It is definitely overused, yeah. I don't know what I'm doing now. Okay, I guess we're gonna code this because I don't have anything more to say about it. Like this is our transition. This is what we're doing. There's not more to say about it. So let's go ahead. I'm going to read in. Okay. So what one letter do I use for the matrix? Let's use. Just mat. So the size of the matrix is at most, they're at most 3 rows and at most 1,000,000 columns. That doesn't make sense. Let's use this. There are at most 1,000,000 columns and at most 3, wait, hang on. Okay, it doesn't make sense for the cache, but, let me figure out the best way to do this. I mean, okay, yeah, sure. Ow, ow, yeah, ow. Yeah, okay. I just kicked my chair. Awesome, awesome. So let's just do this. If n is greater than or equal to 4, don't even read the rest of the input. I recommend that as a habit. Actually, you know what, no, let's not. Let's read the whole input just to build good habits. Because I did recommend as a habit you always read the input, because if you don't, if you break in the middle of reading input and you're doing like multi-tests, you're gonna screw yourself over. So let's just read the whole input. Well, actually, no, it doesn't make sense. Because I don't have more than 4 rows. So if we have at least 4 rows, it's impossible as returned above, and yeah, I agree the samples are not very helpful for this. Right, so otherwise we're going to read in the stuff. I'm going to read into the ith row of the jth column. So I think we've done this. All right, so now once again, the initial state is going to be okay, let's see. If n is 1, another special case, we can just print 0 immediately. Because we might as well, like, there are no even submatrices, so we might as well just not change anything. Otherwise, we're assuming n is between 2 and 3, which is very dumb, but that is the problem we're working with. Okay, actually, dpij is equal to, what is it, 29? You can use memset here, but whatever. And then dp of 0 and 0. might as well say like everything is possible for the left. Like we're sort of creating a virtual column here that doesn't exist, so we can do the transition for the first one. We might as well say everything is possible to make it as easy as possible to have the first column like exist. Might as well do that. So this will be 1. Everything else will default to 0, to cost 0, which is good. So for I equals 0, I is less than m, I plus plus. Whoa. Okay, that's cool. I don't know what that was. That breath in was just whistling. Yeah, you know who blog is very good. I would recommend that. Or at least I haven't looked that much at it, but it seems pretty cool. Alright, so now we're going to iterate over the previous mask. So we're going to use the same for loop. What's the primary endorser in Notepad++? I'm kind of sad that I can't use it anymore. I think there are 2 ways to do it. One says reportedly they've had bugs, so I don't want to mess with that. And the other is a VM, which is very dumb, so I'm not going to do that. Alright, so this is the previous mask. Now we're going to iterate over the new mask. Let's see. Alright, so first, we're just going to convert this to a bit mask. So it's mat j ij times 2 to the j. We're just converting this to a bit mask. So the cost of converting k to, or the cost of converting this column into the bit mask of k is the number of bits that are different, which is the number of 1s in the XOR, and the number of 1s is built-in pop count. There are other ways to do this, but I'm lazy. I don't know. I don't know if it's considered lazy, but this is just what happened. I mean, this is just what I'm using. So it is the built-in pop count of the previous mask of the column and the new thing that we want. So this is the cost. Hello, new total is equal to, for example, dp of ij plus cost. I don't have a mic. I'm just coughing. All right. How's that? Is that better? Okay. So we need to check if this transition is valid, because right now we have this previous column established. Now we're placing down this new column. We need to see if both of the squares are valid. I'm going to create this auxiliary function. This gives you the kth bit of x, because I don't want to type it out a bunch of times. Kth bit of x, return. Gone into this formula so many times already, I don't need to do it again. So it's the bit of, let's see. So we want the bit of like this one. Why can't I think? So it's j. Previous bit is j. So the 0th bit of j, so the pth bit of j plus the p plus 1 bit the p plus 1th bit of j. And the same for k. K, p plus bit k, p plus 1. If count mod 2 is equal to 0, then it's invalid. So if it's possible, then we can finally make this transition. So the new transition, dp of I plus 1 k is equal to, minimum is the minimum of itself and toad, which is the total cost from doing this transition. Final part says I equals 0, I is less than 2 to the n, plus plus, ants equal to min, ants dpm I. Let's see. Multi-tests? No. So it's just not finishing. That's why. Reading the string. Yeah. Because this doesn't go character by character, it goes number by number. Okay. Anyway, I have no idea if this is gonna work. But I was very careful about coding it, so like maybe it'll work first try. There's a pretty solid chance that it doesn't, but there's also like a non-zero chance that it does. And it's in queue. Alright, what's up with that? Have they screwed up the queue again? Does seem like they have. Okay, I guess we are waiting for that one. Okay, so we have 4 left. This one's pretty simple. This one's kind of annoying to code. This one's very simple to code. This one's a monster. Okay. Alright, I'm gonna go to the bathroom though, and then I'll be back pretty soon. Just make like a makeshift. I need to make like a screen for this eventually, but I can like, just put some like binary here or something. Like I literally have no other theme than binary. And then like, how does this look? Then we can like decorate it. It's probably more entertaining than the stream. Okay. I'll mute the mic. Be right back. Hi. Can someone confirm if this sound works? I just want to make sure because I don't know. If I messed that up by turning it off once. Hopefully that did not happen. Yeah, I agree. The queue definitely did suck for the last one. It made the whole round unrated. Sound works? Cool. Problems were okay. I have a different opinion, but I don't know. People enjoy what they will. And that is fine. People have different tastes. Let's see, I'll answer some questions. Yep. Overrule does have a powerful influence on the chat. I am a primary endorser, for sure. Yeah, stuff. How many have we solved? We just did I think. It is in Q, so we have maybe done I. Yeah, quote unquote maybe. So I'm gonna delete this code for now, because if I need it back, I'll just copy from the submission. But anyway. Wait. Now I'm confused about something. Okay. Right. Well, let's just do this. Okay, this is problem J, which I will update now. And I will do that. Replace the pinned message. This one is 2100. Yeah, I'm going to be using recursion. Alright, so this statement is weird, but it like... Okay. So what we're going to do is we're given a list of numbers. We're going to take some subsequence of these numbers. And with this subsequence, what we're going to do is, I'll use their example because I'm a thief. We have, for example, 01526, or rather, let's see, how do I organize this? So we have 01, we have 2, we have 5, and 6. Actually, that's dumb to draw it that way. Come on. It's dumb to draw it this way. Let's do it like this. So what we're going to do is, for each number, we're going to look at this number, and we're going to look at all other numbers. And we're going to draw an edge from this number to the other number that has the smallest XOR with it. So for example, here we would draw a number that has the smallest XOR with 0. In this case, it would be 1. For 1, we would draw the number that has the smallest XOR with 1, which in this case would be 0. For 2, we would draw the number with the smallest XOR with 2, which is 0. For 5 and 6, they would be together. We want a subsequence in which this will form a tree. This is not a tree, it is disconnected, so this would not work. However, if we remove 6, that would work because now 5 would be attached to, no, not 2, it would be attached to 1. And this is a tree. So we want to find the maximum length subsequence that still works. Right, so how do we characterize like the closest XOR? Actually no, okay. Let me figure out how I'll say this. Yeah, it is a good point that there are no cycles. But like essentially, when are we gonna have a disconnect? That's the first step. Let's say, for example, we want Let's say, for example, we have 0, 1, 2, 3. So we write these in binary, we'll get 0, 0, 0, 1, 1, 0, 1, 1. These are going to be together, these are going to be together, they're going to be disjoint. And the reason is because these two share this bit, and these two share this bit. And that's bad because since they do share this bit, yeah, essentially there's nothing we can do. Because if two numbers, like consider like the two groups that are formed by whether they have this bit as 1 or a 0. If both of these groups have at least 2 in them, then these are going to group up together, these are going to group up together, we're never going to get an edge between any of these. So if there exists a bit such that there are at least 2 with that bit being 0, and there are at least 2 with that bit being 1, then we're going to have a disconnect. There is no reason any edge would ever be between these two groups, because it's always smaller to have this. Although, like, it's also important that we're considering, like, the most significant bit. Like, for example, if we have ones here, these are all 1. Or no, not all ones, I guess. If we have, like, for example, something like this, I think this would be fine. Basically, like, if there's some bit that, I guess we do this from largest to smallest. So now we're considering the largest bit. We're asking if the largest bit has this sort of grouping where the two sides have more than 2 each, then it's always easier to avoid having that larger bit because that larger bit is worth more than all the other bits combined to just stick within the groups. So for the first bit, if these groupings were to exist, if we were to have two groups that have more than 2, we have to kill off one of the groups. So for example, suppose we do this. It's fine to keep the 2 because now that we only have 1 in this group, the 2 will have to attach to 1 on this group, and that works out. So now for the most significant bit, for the most significant bit, this grouping is going to work out fine because we kill off one of them. So now we know that this side has 1. But what about for smaller bits? Because now, essentially we're ignoring this bit now because we know it's the same among all of these. So now we have the same set of numbers but with smaller bits. So for example, suppose we had, this is a bad example because we only have 0s and 1s. But suppose we have something like, let's just take all the numbers 0, 1, 2, 3, 4, 5, 6, 7. All right. And I'll just write these out quickly. So initially, they're going to group by the highest bit, so we need to kill off one of the groups. Let's say, for example, we kill off these 3. It doesn't matter which ones we kill off, as long as this is always going to attach to whatever is in this bit. So now we're considering only the guys with this bit having 0. And what do we do about this? So now essentially we're only considering this part of the number. And once again, we have 2 groups here. These will group together, these will group together, that's bad. So we have to kill off another one of these groups. For example, like this. And so it's sort of recursive. We look at the highest bit, we look at the ones that have 1 with that bit and with 0 at that bit. And then we would consider which group we kill off. So maybe we kill off the group with 0. And then now we're solving within the group with 1s and we find the best answer for that group. Or maybe we kill off the other group and then we solve for the best within this group. We have to try both. Both of them are possibilities. Yeah, and then now we're solving recursively for whatever's in this group, and we're trying to find the best answer for that. And we're looking at this bit now. Now, it may initially seem like it's n squared, but the idea is that each prefix is unique, and we're not going to process a prefix of bits more than once. So, for example, we'll process all the bits with 0, 1, and then we'll process all the bits with 1, 0, and 1, 1, and 0, 0. And the sum of all of these is just n because it's the number of things in the array. So the total number of work we're going to do for each level is total n because each prefix is going to be considered at most once. So we have total n. The number of levels is the number of bits we have, which is log. So in total, we do n times log work. Solution by tries, I don't really know how that works. I mean, I'm assuming it's a similar thing. You just you would do DFS on a try or something like that. It's just a different way of counting the information you need, but it's still the same idea. Is there another way with tries? Anyway, yeah, so we're handling this sort of recursively. And we split it up into 0 and 1. Then maybe we look into 0, 0 and 0, 1. And we look into 1, 0 and 1, 1. And we're just taking the best of the answers with them. All right, I don't know what more to do with that. Let's just go ahead and implement. So we're solving recursively for a set of integers. In this case, we'll make it a vector or something. Actually, let's make it a vector. So we're recursing over a specific bit and the vector that we're using. So we're going to group them whether they have 0 or 1 in each in this specific bit. So for LLXA, if the bit they have is equal to x shifted by b and 1, at v.pushback x. So first case is we take the 0. So recurse for the smaller bit. If b is equal to 0, return a dot size. B is less than 0, return a dot size. So recurse b minus 1 and whatever we have in 0. And then what about the other side? Well, it's essentially either if we have anything, we can only take at most one of them, or we have none of them. So it's really the minimum of the size and it's the minimum of the size and 1, because we can have at most 1, but if we don't have any, then we can't have any, of course. And then the other case is the exact same thing, except we do the other size. Maybe we do the other side. I believe that should work. Code might be a bit off. This should actually, I should print n minus that, I'm guessing. No, it doesn't even work. Read an n. Oh, I do not have a base case. if a dot size is equal to 0, return 0. It's less than or equal to 1. Right. Yeah, 4. That's fine. We're finding n minus the answer there. We're maximizing the number of elements we keep. They ask us the minimum number of elements to remove. It's the same thing. Wrong answer on test 13. That's a lot of tests. Alright, looks like that one passed. Let's figure out what's up with this one. How's it going with Mac? Fine. I'm getting used to it. Not much different. I wouldn't say that much better. I haven't really noticed that much that's better about it yet, but it's fine. Okay, something's up with this. If n is greater than or equal to 4, print -1. If n is equal to 1, print 0. Otherwise, we should have some stuff. Mat ji is equal to sj minus 0. Okay, there should not be overflow. That is one thing. For I is, how weak are the tests? That's the thing. So for I is 1 up to m, for j is 0 up to 2 to the n. Make it infinity. Infinity is big enough. Should be. There's no reason to change more than nm values. So for I equals 1 up to m, convert this to a bit mask. M plus equals mat ij times 2 to the j. All right, now for each previous mask, for each new mask, the cost would be the number of bits we change. The new total is the previous dp value for this plus the cost. And it's possible if and only if we check each of the matrices. Yeah. Check the bit in j. This works, right? X shifted k and 1. So if possible, dpi plus 1k. And then dpi plus 1k and that total. So for I equals 0 up to 2 to the n, we take the minimum of dp of m and I. Now, is that somehow invalid? Questioning if it's too small or too large. Oh, it's n by m. Things are up to 1,000,000. Okay, so something is just up here. Test 13 is a pretty late test. It seems to imply something like overflow or something. But I can't see how that would happen because I'm using long longs and everything else is not much different. 2 to the n is not that much. Count mode 2 is 0. Mat ij. Alright, so it's ith column. Am I messing that up somehow? Reading that. It's the ith thing in the jth column. So it's the jth thing in the ith column. I mean, seems like it would be fine. This could also be shifted by j. That's sort of a flex thing you can do. That's the same, it's equivalent. If it's 1, you shift it. If it's 0, you still get 0. I mean, it shouldn't be an issue anyway, because n is at most 3. I equals 1 is equal to m, I plus plus, j equals 0, j is less than 2 to the n, j plus plus, dp of I and j is equal to infinity. That part seems fine. Could this be a problem? I'm overwriting m. I mean, it shouldn't be a problem. Is there any point where I'm using... I am overwriting m, but it's not messing with the value I. That part in particular should not be a problem. dpi plus 1k is the minimum. dpi plus 1k and then tote. Just gonna try some samples. Wait, what? Okay, I don't know what that 26 was, but yeah. I don't know, trying random things. 37. There is a time to massage the stress test, but I don't think it's now yet. And pop count of mx or k should be fine. Is the initial thing messed up? Don't see how it could be. So if I want a particular column, I will check the cost of getting that particular column. So where could this be going wrong? I solved this problem before. So maybe I'm just missing something. Or it's just some typo. Typo is the most likely scenario. This is not problem J, I'm back at problem I. Hopefully it shouldn't take long so I don't have to actually update the thing. I don't know. with my already existing tiredness, staring at the code is probably not the best way to debug, but I don't know, I'm feeling lazy today. So let's use something else, I guess. I don't think this changes anything. In fact, this should not change anything. Being shadowed is fine. Something messed up here. Is there a function called bit? No, okay. Count mod 2 is equal to 0. Yeah. If it's possible. It should be the minimum of whatever the previous thing was. Could it be a problem with the 2? What would the problem be with the 2? Why would that specifically be a problem? I'm not handling 3 especially differently. Should be 2. Just gonna making sure that even length square submatrix has an odd number of ones. Alright, p equals 0, p plus 1 is less than n. At here, this 2 would be n equals 2, p equals 1, 2 would be not less than 2, so it would break. I'm specifically making it return 1. X shifted K. It's actually a pretty subtle typo. So 0 up to n. Just gonna look at each piece of the code, I guess. Well, that's what I've been doing. I don't know why that would help, but I can hope. There's always the potential to hope. At some point I'll get bored and I'll look at the test. But I guess not yet. DPIJ plus that cost. K is up to 2 to the n. K is up to 2 to the n. I'm shadowing something else. Built-in pop count of masking K. Mask XOR K. The number of different bits. The number of bits we have to change. Some subtle typo. Subtle that's not, it's like it makes it to test 13 somehow. Okay, for the sake of stream, I'm gonna look at the test because we have more problems to do. Normally don't recommend this though, but for the sake of stream, I will. Oh, okay. That's what it was. Yep, right. Awesome. That is very cool. Very cool bug. Awesome. God damn it. Why did I let that happen? It's printing 0 twice. That's what happened. So yeah, some subtle thing usually that gets you. Okay. We're done with this now. I looked at special, like I had that special case, I just forgot the return. Oh my god. Okay, now we're gonna do the problem of the K. That is the problem K. Okay, cool. Let's just put that behind us. Yeah. Okay, so this is the hard version of an interactive problem. The easy version, I don't think is like, I mean, there's some merit to it, but including both is just sort of dumb. So, basically, you're trying to guess an array, and you have the powers of, I didn't include the deltix one. Yeah, because that one was sort of repeated. You have an array, you have the powers of asking certain questions. The questions you can ask are the XOR of two indices. Also, I'm going to load these problems in advance, just because code forces might go down, which is not what I would want. You can ask the XOR of certain indices. You can ask the AND of certain indices. You can ask the OR of certain indices. And that's what you got. You want to guess the whole array using at most n+1 queries. You have at most n+1 queries. Right. Now, the first thing you can do is, it helps to, the first thing we'll do is, suppose we know A0 XOR A1, and we know A0 XOR A2. We know A0 XOR A3, and etc. Using this as our basis, what we can do is we can use this information to get the XOR of any pair of indices. For example, suppose we want A1 XOR A4, we can do A0 XOR A1 XOR A0 XOR A4, and this would give us A0 XOR A0 XOR A1 XOR A4. This comes out to 0, so we're left with just this. So we can use this to get the XOR of any two numbers. So this would take n-1 queries, leaving us with 2 left. Okay, now another thing is, suppose we know two numbers are equal. If A is equal to B, then A and B is equal to A or B, which is equal to A and B at the same time. So the bitwise AND will be equal because all the bits are the same. The bitwise OR will be equal because all the bits are the same. So what we can do with this is, if we can identify that any two numbers are the same, then we're golden. And the reason we're golden is because if we can find a single number, then because we can find the XOR of this number with everything else, we can automatically find the numbers like with everything else. Like, for example, we can know, suppose we know A2. What the hell was that? Suppose we know A2. Then to get A3, we can do A2 XOR A3 XOR the number we know, which is X. And these two will cancel out, so we're left with A3. And because we specifically know the value of A2, we can cancel out A2 and we can be left with A3. I don't know why I made this a superscript here, but yeah, that's the idea. So as long as we can find one number, we're good. Okay, so the problem is, what if we can't find equal numbers? And what we do with that is, so, okay, first of all, to find the pair of equal numbers, if A0 XOR AI is equal to 0, then A0 is equal to AI, because all the bits are the same. So that's our pair of equal numbers. Otherwise, nothing is equal to A0. So maybe something is equal to the other ones. So for example, A0 is equal to a, well, actually, what we're doing now is we're looking for two pairs that have the same XOR with A0. So for example, if A0 XOR AI is equal to A0 XOR AJ, well, we can cancel out A0 and then we can conclude AI is equal to AJ. Yeah, so in that case, that's a J. So in that case also, we have two equal numbers. So those are our methods for finding two equal numbers. If we find two equal numbers, we can query their AND, and we'll be done. We will find it in AND queries. But what if we don't have two equal numbers? As it turns out, we can still extract some numbers that we want. But we just need to split it up. So we don't have two equal numbers, but what it means is because we have n numbers and the numbers are up to from 0 to n minus 1, it means we have a permutation. It means every number will appear exactly once. So what we need to do now is, we're going to, normally we would take the bitwise AND of two numbers, and that would be that. We would find out all the bits immediately. But we don't have two equal numbers, but what if we found the bits in a different way? What if we found, for example, one bit in one query, and then the rest of the bits in another query? Probably because we're at the later problems and people are losing interest. But we have one bit in one query. So for example, like 0, 0, 1, and like 1, 0, 1 or something. So we can find out using the XORs that these two numbers have the same first bit. And if they have the same first bit, then we can find out what that first bit is using the bitwise AND. And using this pair of numbers, we can find out the first bit for every pair of numbers. This is also because bits are independent. Once again, another application of this idea. And we know this is true because we have a permutation. So we have every number that has the 0 in this bit, and we have every number that has the 1 in this bit. So with the permutation, we can do that. And what about the rest of them? Well, once again, because we have a permutation, we know that For example, for 0, 0, we know that we'll have the number 0, 0, 0, and we'll have the number 0, 0, 1. So as long as we have two numbers that have the same value of the rest of the bits, ignoring this, then we can once again use our query to find out the values of all the rest of the bits. So we're sort of splitting the information up into two queries. We're using one query to find out the smallest bit, and then the other query to find out the rest of the bits, instead of doing all the bits at once. And it's a bit like more annoying, but overall it's like fine. So that's what we're doing with that. Yeah. That should be good. It's kind of slightly annoying to implement, but I guess it's not the worst. The way I'm going to implement it, even if we have two same numbers, I'm just going to pretend that we're doing the same strategy where we use one bit like that and the other bit for the rest of them. Even if the pair is the same. Yeah, I know Kofers will be down. I might not be able to do M. That is kind of unfortunate. That might just have to happen. Because I don't think I'm going to be able to code it within the time limit in time. So I guess we'll see. You might miss the coding phase of it. Anyway, so let's try and implement this one quickly, though, although I doubt that's possible. So cn to n. I don't think I need this actually. So we have a value of 2 to 16. It's up to 100,000. So query 1 I plus 1 and L cn to vi. We're automatically using the v0 is equal to 0. Okay, so first find two equal elements. So for I equals 1, I less than n, I plus plus. If vi is equal to 0, then first is equal to I. No, wait, we need pairs. First is equal to 0i. Yeah. First is equal to rest. Break. So we're storing this. If we find a value with XOR 0, it works with the first value. Otherwise, if we find two equal values of XORs, then it works. Otherwise, so if first dot f is not equal, so we know the permutation. Right, so the first thing is we need to find something with the same the same last bit. Dude. Actually, what we can do here is, because we know that the A0 is a value, we just need to find something that works with the index 0, and that should work. Because if it works with the index 0, then it must, because we have a permutation, so we have to have like every value, and one of them is going to work with the index 0. So, I swear to God. That indentation is kind of annoying. So, I don't understand what that is. If vi and 1 is equal to 0, note precedence. Then it means we have the same bit. So first is equal to, First is equal to 0 and I. Break. We do the same loop, except now we're looking for anything that matches the rest of the bits. So we're saying if vi is less than 2, that means that only the least significant bit that we've already accounted for is set. In fact, we can specifically ask for 1, because we know we have whatever this number is, but the last bit is different. Again, because it's a permutation, we have every number. So we do that. Actually, wait. What derivative of the bit? So for b is 0, b is less than n, b plus plus. We're going to say target to go first on it. So for I less than 0, I less than n, plus I is not equal to targ. Make the bit function again. Shift K and 1. So for I is 0 up to n, if I is not equal to targ, then what? So AI plus equals, so it's the bit of targ, it's the bit of val and I, Actually, we don't need if I is not equal to targ. So it's the bit of val and I XORed with vi XOR v targ. Shifted by b. No, this should be val and b. The bit XOR vi XOR v targ. Right. So this is saying for the 0th bit, use the first ones, which we decided were for the 0th bit. And then I did not pin that. Good point. Okay, that should work. For the 0th bit, we use that. For the 1th bit and above, we will use the last value because the last value is what we decided to determine the 1th bit and above. So then let's do like 17. It doesn't matter. We'll go up to 16. What do I have to print? There's something about like exclamation or something. Yeah. Alright, we'll use the array 0, 1, 2, 3. F. Okay, I'll use rest. Sure. Rest, 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 rest. So we use the array 0, 1, 2, 3. So 4. Alright, so this is 1, this is 2, this is 3. So AND of 1 and 3 should be 0. AND of 1 and 2 should be 0 as well. Okay, what did I mess up there? That looks wrong. Slightly wrong, yeah. Oh wait, that's why. It should be bit, it should be the bth bit of that. XOR the bth bit of that. Okay. It's 4. So 1, 2, 3, 0, 0. There we go. Okay, I'll just screw it and submit because we're sort of running low on time. A decent chance it gets out on this limit exceeded and just dies. I can see that happening. Yeah, test 2. Okay. Test 3. Test 11. Saw test. Okay, we're fine. Alright, that leaves 2. I already opened this. That's a lot of tests. Wow. That is very much a lot of tests. It is still going. Okay. Yeah. Time limit is 4 seconds for a reason. Okay, that leaves 2. When Code Forces is down, I will be sad. Yep. We have 17 minutes. I doubt I'll be able to get to M, to be honest. So, I don't know. I don't know what I'll do about that. I am perfectly fine with never doing a video on that. That is something I'm okay with doing, because screw that problem. But if I have time, I will do it. If Code Forces happens to go down a bit later than 3, that would also be fine. So let's just let's do what we can. Enormous XOR. This is basically like sort of a logical problem. And the code is actually just very simple. It's just implementing the formula you figure out. You're given 2 integers L and R. By the way, this is a bit similar to this one, except you're asking for the range of values instead of the XOR for the pair. So it would be this problem, but it's the XOR of A plus 1, A plus 2, up to B. You want to, so you have 2 numbers LR, you want to pick 2 numbers X and Y, and you're going to take the XOR of all numbers between X and Y, you want to maximize it. And get the binary representation. So some special cases right off the bat. If L and R have different bits, have different first bits, and then you can do 0, 1, 1, 1, 1 for L, and you can do 1, 0, 0, 0 for R, and you're done. So Cn to N to S to T. Also a special case is if T is equal to 0. S0 is not equal to T0. Else. And this is the crux. So if they do have the same first bit, then what we want to do is well, the best thing we can do is we can have an odd number of numbers between everything. So for example, suppose L the binary representation of R does not contain any extra leading zeros. That is important. Yeah. So I actually kind of forgot how this works. So we're supposing L and R actually no, that's not exactly valid. Let's see. Suppose L and R match on a prefix. So for example, L is equal to like 1, 1, 0, 1, 1, 1, 0, 1, and then they both match on this prefix. If they don't match on anything, like if this starts with a 0, then we handled that. That's a special case. Otherwise, they both have a 1. And if they both have a 1, that means that for this to work, we need a range of odd size. Otherwise, there's nothing we can do. But the key idea here is what is the key idea? The key idea is when we take a range of odd size, let's say we take X, comma, Y. So X and Y will both be same parity because we want Y minus X plus 1 to be odd because we want an odd number of numbers. And if we can only keep this bit if we have an odd number of numbers. So we need to do that. So X mod 2 is equal to Y mod 2. And so suppose like x is even. If x is even, then you get x plus 1, y plus 1. No, sorry. X plus 2, x plus 3, dot, 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 y minus 2, y minus 1, up to y. And what we're going to do is we're going to pair the even numbers with the odd ones. And the reason we're doing this is because an even number plus 1 is an even number XOR 1. X plus 1 is equal to x XOR 1. And it's because the smallest bit is missing, and when we add 1, we just add that bit to it. So really, actually I'll keep that. Because this is true, these numbers are all going to sort of cancel out. So for example here, these will XOR to 1. These will XOR to 1. Everything here will XOR to 1. These will all XOR to 1. So the only number that doesn't get canceled out is y. So what happens is maybe we modify the last bit of y, or maybe we don't. And suppose x is odd, then we can do the same thing. We start off with x, which is odd. Then we get x plus 1, x plus 2, can't draw, dot, 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 y minus 1, y. And once again, we can group all these numbers together, and all of them will cancel out to 1 except for x. So really, all we're doing with our selection is we are picking a single number, and maybe we can modify its last bit to be 1. The question is, can we do this? So the number we would want to pick is, of course, the largest one. So we are considering the largest bit. We're considering taking r, because again, the best we can do is some integer, and maybe we change its last bit. So the best thing we should try to do is r, because r is the best we can do, regardless of whether we can change its last bit or not. So the question is, can we change its last bit? And well, we can figure that out fairly easily by just seeing how many integers we have on the range r minus l. So we need to compute r minus l plus 1, or more specifically, we need to see if it's at least 3. So the question here would be, is it at least 3? So first, because we're considering r minus l, we can sort of ignore all the parts where they're the same. So if s is equal to t, cout. Actually, I'll do string lr. That should be easier to follow. So if r is 0, yes, l0 is not equal to r0. If s equals t, print t, because there's not much better we can do. There's literally nothing better we can do. Now we just need to see point is equal to 0. While point is less than n, and the two things are equal. I just used s and t again. I don't know why I did that. L point is equal to R point, increase point. We know they're not directly equal. So now we're at the point where they're different. And because R is greater than L, this must be a 1, this must be a 0. So the only case where R does not have, the only case where we do not have 3 numbers is if this is all zeros and this is all 1s. In any other case, we're going to have more than 2 numbers, because this is exactly 2 numbers. If we're any less than this, we get at least 1. If we're any more than this, we get at least 1. So the only case where we cannot change the last bit of R is in this case in particular. So then in this particular case, plus plus. So by like going up until they're not the same, we will have stopped at this point. We don't care about this point. We're interested in the stuff after it. If it's all ones or it's all zeros. If it doesn't exist, then we also only have two things. Like if there's no more string after this, then we also only have two things. So the question is there any non-1 in L or any non-zero in R? So I is equal to point, I is less than n, I plus plus, bad, and equals Li is equal to 1. So if any of them are not 0 or not 1, then we're fine. If not bad, R m minus 1 is equal to 1, and then we print R. Because we can change the bit, of course, we would want to make it as large as possible, so we would want to make it 1. So that's the idea. A lot of cancellation, and ultimately, we can barely change R at all. Come on, finish. It's just not running. Okay, I'm gonna test 7. Alright, if this passes, that is a 2600 in 13 minutes. Yep, this is a 2600 rated problem. And it it is literally a yes-no problem. But the concept of cancellation is pretty hard to get, so I get that part. This idea that only one number really matters. But yeah, that is indeed a 2600. So the implementation is very easy if you want to grab a very hard problem under your belt. Or like relatively hard. Alright. Now we are done with everything except M, and I'm not going to be able to implement M in 5 minutes. So what I will do is, I will... How long do they say coforces will be down? Let me open an incognito. Okay, 2 hours. So definitely not going to continue with that. Physical Hacker Cup round 2, that is indeed next week, I think. I'm pretty sure. Yeah, I will definitely be doing that. Because I can get the shirt from that. So we just really need like top 500, I believe, is the cutoff for round 3. And then from that, top 200 in round 3. And then finals is unlikely, so that'll be it. Yeah, top 25. Okay, last problem. You have an array. You can do a bunch of operations. In one operation, you can pick an element, you can add it to another element, and then remove the element you just picked. Next stream might be next week. If I wait, hang on. Okay, Hacker Cup. Come on, Facebook Hacker Cup. Yes, it's on Saturday, right? Yeah, it's on Saturday, so I can do the stream on Sunday. That would work. Right, so in this, again, you can pick an index, add the value at that index to another value, and then remove the value at that index. And then you want to do the minimum number of operations to make the array strictly increasing. So this is another instance of bitmass DP, except there is this. You can see how they tried to balance the time here by like saying like there is some stuff going on here, there's some stuff going on here. They limit the number of huge cases, then they limit the number of stuff with n equals 14, then they further limit the stuff with n equals 13, then they further limit the stuff with n equals... God, it's crazy. Yeah, it's crazy. So, The intended complexity, by the way, is O of n squared times 3 to the n, with some constant optimizations and stuff like that. So I will go over this. Here's my plan. I will go over the solution to this. If Codeforces is down afterwards, I will stop the stream. If not, I will try and implement it. We will finish off with this problem. I will go over the solution no matter what. So the idea is we're going to select. So the idea is it's bitmass dp. And the first part is saying, the first part of the mask, so what do we have? What do we have in this dp state? The first part of this mask is whether we've taken an element or not. In particular, like, or not whether we've taken an element, like, actually, yeah, whether each element has been taken. Let's see if this is down yet. Not yet. Okay. So this is the mask of the elements that have already been used in the final array. So for example, suppose we have something like this. Maybe maybe we're saying that this is going to be specifically an element that we keep. And then maybe we're going to merge these two into it. So these two elements have not been touched at all, but all of these three have been considered in terms of the final array. And then also, we have to make sure that the elements are in order, because we need to make it strictly increasing. So what we're going to do is we're going to store the last index that we took for the final array. So for example, like here, this last index will be this one, because this element is part of the final array. So any new element we take has to be further along. I believe that's actually all we need for the state. The transition is also painful, because the transition involves putting a new element on. The transition involves putting a new element on, and we also have to iterate over what we put into that element. So for example, we choose some specific mask that we're going to use. Like for example, we say, let's add some more elements on. We say we're going to merge all of these indices together into something. That is one possibility. We can choose every possible mask, the remaining mask of the elements that we have yet to take. So for example, all of these have been taken already. Of the elements that we have yet to take, we can take some submask of those elements, and we can merge them all into a single one. The question of which one we merge into is automatically answered. We can do it greedily. We would greedily merge it into the one that's the smallest one that's still after the previous one. And that's the number of merge operations we do. Right. I believe that's it. So taken has value, has 2 to the n possible values. This has n possible values. Then the mask you iterate over has, as it turns out, it is 2 to the n minus pop count of taken. And I did go over this identity that the sum from I equals 0 to 2 to the n of pop count I, or 2 to the n minus 1, not including n, of pop count of n is equal to 3 to the n. I went over that in the video. I'm not going to describe it again. But that means that the total number of pairs taken mask is around 3 to the n. Which means that the total number of time we will spend transitioning is 3 to the n times last times something else. In particular, if we spend O of n time trying to figure out the index that we merge into, that could possibly contribute another factor of n. However, you can speed this up, and I'm already thinking of constant optimizations. You can speed this up by iterating over. You can pre-compute, if we have a specific mask that we're going to merge, and we have a specific previous index, what will be the index that we use to merge into? This can be pre-computed, and it will save a factor of n. I'm assuming there is also some more constant optimization that must be done. Coforces is still not down. I mean, I could try to do it. It's going to be very painful. But nobody's going to have a good time. So we'll decide right now. Do you guys, you want me to do this? Actually, yeah, I guess I should. I guess I should attempt to. And also, of course, there's the pain of restoring the operations. I think I'm just going to write the DP first, and then I will handle restoring the operations after. Oh yeah. And this will specifically store the smallest value of last. Which is important. This stores the smallest value of last, and that's important because because otherwise we don't know what the actual value is that's here. So we want the smallest possible one because it's, again, sort of greedy that we don't, we want to be able to merge as easily as possible. And a smaller value will let that happen. So let's see if we can do this. I doubt it, but let's see if we can do it. Alright, so dp of 2 to the 15th and 15. Might have to make this int? No, 10 to the 6th. Yeah, okay. We'll see. We'll see how far down the constant optimization rabbit hole we get. Oh wait, I missed something. We also need the number of merges we do. I missed something. We also have the length of the array here. That's also part of the state. Yeah. So that's where we get 3 to the n times n squared, because we have 3 to the n transitions and n squared possibilities for each of that stuff too. So it's dp of taken, last, and length. Then we're going to store the previous state. So now let's see where we're going. We have multi-tests. because screw you. And 4 I equals 0 is less than n, I plus plus, c into ai. Now, somehow we are going to figure out how to do this ordering. Let's start by writing it naively, and then later on we will see how bad it does. So this is, we're going to iterate over the mask of taken, 2 to the n, I plus plus. I'll do t for taken. Then for last equals 0, last n, if taken has that bit, I'm also counting the number of ones, and that's because we can iterate size. We'll do B for size, I don't know. S for size, sure. 0, S is less than or equal to size, S plus plus. Reasoning here is the length can be anything from 0, I guess 0, to, like it can't be larger than the number of elements we've already considered. Okay, so the rest of the bits is the complement, which is 2 to the n minus 1 minus the mass that we have. These are the bits that have not been considered in the array. Okay, so this is taken elements. And then this is size of array. Now we are going to iterate over what? The new mask that we take. M is equal to T. No, that's not right. I'm pretty sure this should work. This is sort of a bit of black magic to iterate over all submasks of T. It's not actually that black magic. It makes sense if you think about ignoring the bits that aren't part of T, then it's just normal subtraction by 1. Anyway, I don't know. That's too much to oh, Code4 is already down. Alright. Well, okay. Here's what I'll do. I will finish coding, I will make it work for the sample, and then we'll be done. Obviously I can't submit now, but I will finish the code, and then later on, I guess I'll post an update on how that's going or something. I imagine it'll be terrible. We'll see. So this is the new mask. What is what? This is the intended solution. I checked my solution with theirs just to make sure I wasn't gonna be dumb on stream. Did you have a better complexity? I don't know what you mean. Oh wait, that should not. Right, I forgot. I forgot that. Okay, yeah, yeah. Yeah, I totally forgot about that. Right, forget that like ever happened. Dude, I've been going for 5 hours. All right. Yeah, forget that. Yeah. Yeah. Right. Totally know what I'm doing. Yeah. Okay. I think I don't need the comparator there. Yeah. I would have realized that eventually, I think. Yeah, I don't know what I'm doing. Okay, so now that we do that, we're going to use this pre-computed value. Okay, we'll do this pre-computation. Now for I equals 0 is less than 2 to the n plus for j equals 0, j is less than n. Actually, this should be up to 16 because we're going to feed from the last index of that. This should also be 16. This should be 16. This should include the value 15. That's equal to n. If this bit is set in wait, if this bit is set in I, should be j plus 1. Best is equal to next I j is equal to k. Best. We can do that more efficiently, but this is just 2 to the n, so it doesn't matter. Right. I'm just also going to pre-compute the sum of all masks. Lazily, because it doesn't matter. There's some efficient formula that works in 2 to the n, but I really don't care. S plus equals a j. Sum s. I don't really need the variable s, but I don't care. If I shift by jm1, s plus equals aj. Best is the minimum, best, okay. Right. So if that's another optimization. I can sort these new masks by sum. Okay. Wait, actually that might be worse. whatever. That could potentially be worse, but it would lead to an early break, so that could happen. If sum of mask is greater than dp of t ls, then the new thing is if dp of t or m, bitwise or m, the new last index is I'll do this for clarity, though I think it's faster to not do this. Then I is equal to next of next of m and l, and the new size is 1. Again, this probably makes it slower. Oh yeah. And then dp of 0, 0. That's a pain. That is a pain, huh? Yeah, it kind of is. Okay. Well, what's with that? I guess we have to make this 17 now. 0, 0. We should one index that, I guess. So right, now this goes up to n. So what does this imply? So it's next of m and l minus 1. No, it just means this. Right? So this is 0. I'm so lost now. So there's a greater index greater than or equal to that, which is fine. It means it represents that minus 1. Do I need to one index here? It represents before 0. Okay, the problem is like, do we need to one index? I don't think we do, because if last is the last index anyway, then it's fine. Yeah, wait, okay, I don't need to one index, so this is fine. Is greater than sum m. Then we need to do some stuff like this. So this would be equal. Par. Wait, this should be like massive. Yeah. equal to n, equal to n. dpijk is equal to 189. Yeah, the stream video will be available afterwards. So then par of nm ni is equal to what? So this is L, no, T and L. Sure, we'll store the previous index and then screw ourselves over later. Right, okay. It's like, this should theoretically work. 15, wait, 0. If dpijk is less than or equal to 28 or something, ants is equal to max ants pop count I. Sure. 3 errors, okay. Sure. What else? Reference to next. Control F. Next. Place all. Happy? Yes. Okay, that did nothing. Yeah, that did literally nothing. What the hell is that? Oh, wait, it's because it shouldn't be popkin, it should be K. I guess. Where does it make a difference then? No. Right, okay. We're trying to maximize the length of the array. Oh, wait. There should be N. There should not be I here. Yeah, that is a mistake. Alright, so dp to the n. I don't know why I'm doing pop count of k. That shouldn't make a difference anyway. This would still be wrong, but yeah. Let's just print everything. dp tls. see if where the numbers are dying. It's not even printing anything. And wait, this should be rest. That makes sense. Close Safari, please. I really hate that it's showing that stuff. Okay, still. Awesome. So we'll do some stuff like this. Okay, that's fine. Well, okay, so all of them are massive. This doesn't help matters. Well, I'm trying to look at this case. This is 8. All these samples are big. Man. It's not pushing out anything. Wait, why? Why are you not iterating? Oh. That makes sense. Okay. So I guess we don't need this check. Let's comment this out for now. We will need a form of it for probably some constant optimization later, but for now, let's just see. Okay, now we're getting actual values. Now we're printing everything. Okay, this is absurd. Let's stop. Get rid of the prints. Five, 8, 1, 14. Looks right. Okay. Okay, we're good. We're getting the answers right. Now we just need to do the operations. If k, yeah, I know the submission won't work. I'm just gonna code this, make it work for the samples, and then test stuff out later. But yeah, I can't do much better than this right now. So if k is greater than the answer, then answer is equal to k, targ is equal to 2 to the n minus 1, j and k. Now, while targ 0 is greater than 0, k is equal to parent of targ 0 and targ 1. This matters too. So, and targ2. So it's, the mask we're using is p.f xor targ0. Anything that's in p.f but not in the new mask. So then the final update is targ0 is equal to p.f, targ1 is equal to p.s, minus targ2. So the into is targ1 for I equals 0 as an n I plus plus. If diff this ith bit is set, if I is not equal to into, ops.pushback okay. I'm aware that the numeration will change now. Honestly, I don't care. I will fix that after, but after this stream, I'm just gonna like be done for a bit, and then I'll fix this code to like fully work afterwards. So ops.pushback is an index. So we move I into j. So it should be I into. One 15, 2 14, 3. Yeah. Seems like it works. 1 2 1, 3 8 6. Wait, what? So move 8 into 6, so you get 7 here. So 2 1 3 5 1 7. Move 2 into 5. 2. Okay, seems like it works. Okay, all right, that is the stream. I will finish this off later, but I think that is enough for now. I think we've pretty much satisfied everything we wanted to do. We went over the whole mashup. Yeah, that's it. So yeah, as I always say, the stream will be available afterwards. It'll take a while to be up initially, but afterwards it'll just be up forever. And the mashup will be up forever. Everything will work as soon as Codeforces comes back. Okay, if you have any questions, I'll talk to you like after the stream. You can talk to me like right here in this Discord if you want. Feel free to just join if you have extra questions or stuff like that, or just like anything. All right. Yep. Once again, thank you for the first dono. That is awesome. You can still see the aftermath right here. I don't think I get all of that, but it should be like a pretty decent chunk. All right. Goodbye, all.